Okay, good afternoon, everyone. So I welcome all the participants for this E&ICT online faculty development program on optimization technique, theory, practice, and emerging applications, which is starting from today, that is 30th January 2023. It will continue up to 8th February 2023. So this faculty development program contains 20 lectures. So the first lecture is from 3 p.m. to 5 p.m. and second lecture is from 5 to 7 p.m. So the lectures are either theoretical or it is hands-on, or it is theory followed by hands-on. So whatever best possible, all the materials and videos and other things in view mode will provide to you, so that later point of time, if you want to revise, you can do that one. And we have also some lectures from some resource persons from outside NIT Warangal, like Professor Prakash Kotecha from IIT in Guwahati, and we have Dr. Akhtar Khan from IIIT DM Kurnool, and Dr. Sarath Naik from Yonsei University, South Korea, and Dr. Lab Kumar from NIT Kurukshetra, and Professor Saroj Kumar Patil from NIT Rourkela. So some lectures may be purely hands-on, and some lecture maybe you have to do hands-on calculation also. So I request all of you to first install MATLAB, and also you have to with a calculator, scientific calculator. If not scientific calculator, you can use your smartphone calculator for doing hands-on calculation. So if any specific software is required, I'll let you know so that you can install one day before. And one more thing related to this FDP, we have 74 participants. We usually have 50 participants to run a particular course, but there is a huge interest in this particular course. So we are running this course with 74 participants, and a few participants are from abroad also. So it is really a good program. I hope you will understand the basic concepts and basic algorithms and their implementation in this faculty development program. So this course is sponsored by E&ICT NIT Warangal. So it is a 40 hours program. All the programs conducted by E&ICT all are 40 hours program. So either it is in 8 into 5 mode, that means 8 days, 5 hours per day, or we have 10 days, 4 hours. So for convenience of the participant, we have made it 10 days, 4 hours per day. But earlier we used to have 8 days. For each day we have 5 hours, but now we have reduced it to 4 hours for it is easily interactions and for easy understanding of the program. This is all about the course. If you need anything, or if I miss something you want to discuss, we have a WhatsApp group also. I have sent the WhatsApp link to all the participants. If any participant wants to discuss anything or ask anything, you can post in that WhatsApp group. We can discuss over there. So coming to the first session, I welcome all of you to again for this first session, which is on non-traditional optimization method. So this lecture will give you the brief history and brief introduction related to all the optimization methods. And gradually we will see detailed about the different optimization methods in upcoming session. And in this session also, I'll more focus on the genetic algorithm, one of the very popular optimization or soft computing method. And also we'll see some of the application while describing different phases of genetic algorithm. So if any point of time, if I missed any point, or you want to discuss something, you please interrupt me. You can unmute or you can write in the chat box. So I'll address your query before moving to the next slide. So as the name suggests here, non-traditional, that means the optimization methods are not new. You can see there are a lot of optimization methods are there in the literature. But if you go to such methods, you will face a lot of difficulties whenever you are dealing with a very complex problem. So in order to avoid that, we have various non-traditional optimization methods. So first we will discuss about the basics related to an optimization method. Then I will directly go to the history of genetic algorithm and application of genetic algorithm. And we will see detailed about the steps of genetic algorithm. Basically, we'll discuss a flowchart. We'll follow that flowchart to understand different phases or different components of the genetic algorithm. So if you go for a complex problem, generally complex problems are also called as your large scale problems. Like if you want to do with any scientific problem or if you want to solve any engineering problem. So you will see such problems are having numerous variables, and such variables are also dependent on each other. So in that case, if you apply the traditional optimization algorithms, you will face a lot of difficulties. Like suppose I'll write a equation here like x1 plus 2x2 minus 3x3, which is greater than equal to, let's say, 10. Okay, I have specified some boundary for x1. Boundary means you can say a lower limit and upper limit. For x2 also I'll specify the lower limit and upper limit. X3 case also I'll specify. And suppose I have written x1 plus 2x2 is greater than equal to 10. So here, if you see this particular example, we have three different variables. Okay, for that we don't know what is the particular value for these three. So it looks very simple because only we are dealing with the three variables. But when you go for a large scale engineering problem, you will see the number of variables are quite high. So if there are three unknowns are there, you know, we require minimum three different equations to solve that particular set of equations. So when you map with a large scale problem, suppose you are dealing with 100 different variables. So it is very difficult for you to solve that particular problem. That's why the traditional methods like linear programming, dynamic programming techniques, they are failed to solve such complex problems. And the major difficulties with such problems is not only with large number of variables, but the objective function of such techniques is non-linear. So as the objective function is non-linear, it is very difficult to determine the global optimum. If you want to minimize a particular problem, then you have to achieve the global minimum. If you want to maximize it, you have to reach the global maximum. So as the objective function is non-linear, so the local optimum is not necessarily the global optimum. And sometimes we reach to the local optimum or we are failed to solve the particular problem. So in order to avoid such difficulties of linear programming or dynamic programming or such type of methods, we have non-traditional optimization algorithm. So our basic objective in the non-traditional optimization method to reach the optimal solutions to the problem. Our solution should be close to the global optimum solution, whether it is a global minimum or it is a global maximum, based upon whether it is a minimization problem or it is a maximization problem. So now, as I said, the objective function is non-linear. Let us compare two different objective function. One is a linear objective function, another is non-linear objective function. So with a small illustration, you can see with these two figures, you can understand what do mean by a linear objective function and what do mean by non-linear objective function. Like I mentioned, traditional methods are non-linear objective function. As it is non-linear, so I said local optimum is not necessarily a global optimum. But when you go for linear objective function, the local optimum is same as the global optimum. That is the advantages if you get if your problem is linear. Moreover, linear means anything related to the line. Line means you can say y is equal to mx plus c is the equation of a line. So if you can, like if you go for linear regression, or if you go for a variant of linear regression, that is multiple regression, in such cases, our objective is to draw one or more lines. Okay, like I can say if the value of this is your x-axis and this is your y-axis. So if the x value is increasing, y value is also increasing. So more or less it is related to the line. So in such a case, you can see optimum is always attained at the constant boundary. You will find the optimum value in the boundaries only. But when you go for nonlinear objective function, the optimum may be the interior part or it may be the boundary of the constraint. So that is the main issue with the traditional methods, which can be avoided by non-traditional optimization methods. So when you go for non-traditional optimization methods, mostly these methods are either biologically inspired or these methods are based upon nature, based upon the animal, based upon different behavior of different objects also. So these algorithms, okay, if you go for non-traditional optimization algorithms, mostly they are stochastic in nature. Stochastic means the randomness is present in such type of problem. Like if I ask you, generate a random number in between 0 to 1, right? So you can say the random number may be 0.5823. The random number may be 0.6388, right? So these are nothing but the randomness. So when you go for such type of optimization problem, you will find whatever result you got in a particular case, in another case you may find a different result. So with respect to different iteration, you will get a different result. You will not get the same result. But over a period of time, if you go for 50 iterations, 100 iterations, like that, you will see more or less all results are same. Okay, you may get the result in one case in 48th iteration, another result in 52 iteration, but the values are more or less if you go for a large size of the iteration. But the principle behind such a optimization method is the combination of two extremes. First one is you have to reach to the global search, right? For example, a source space is given to you. In that source space, you want to find a particular solution. You don't know where your solution lies, and your source space is very, very large. In that case, you can apply optimization method. So what we can do here, we are trying to get a global search, which we call it a random search. It is also called as extreme exploration. So you have to reach each and every part of the sample space. At the same time, also, you have to trying to reach to the local search. For example, if I say the solution lies at this particular point, then you will go for a local search in order to find the optimal value in that local search. But in order to reach this point, you have to make a global search. So basically, these two principles are having trade-off to each other. So if you make the global search, it will going to impact the local search. If you make local search, it may impact the global search also. So you have to balance these two. That is random search as well as hill climbing. You have to balance these two to find a particular solution of a particular optimization problem. So over a period of time, when we discuss this thing, it will be more clear to you. So if you go for categorization of these non-traditional optimization methods, then you will find there are three major groups or three different groups you can divide all the optimization methods. And most of the optimization methods mentioned in this slide or the next slide is going to be covered in our faculty development program. First one is called as evolutionary algorithm. Under evolutionary algorithm, we have genetic algorithm, we have genetic programming, we have evolutionary programming, evolutionary strategies, differential evolution, bacteria foraging optimization, and artificial immunoalgorithm. This is belongs to one category. Not necessarily all the optimization algorithms are listed here. Like if you go in your respective domain, you will find a lot of optimization algorithms are designed every day, right? Today you will find a new type of optimization in your respective research area. So it is difficult to list out all that type of optimization algorithm. Rather than you have to understand what is the main methodology behind that such type of optimization. Like I told you, mostly all are called as stochastic optimization. In each and every optimization, you will get some kind of randomness. Without randomness, you cannot say that this is an optimization algorithm. Whether you choose genetic algorithm or you choose evolutionary programming or bacteria foraging optimization, all the optimization algorithm, you will find there is a randomness. Now, the second category is called as swarm intelligence algorithm. One of the very popular algorithm under this is called as particle swarm optimization algorithm. Basically, if you see in any research domain, you will find when people solve multi-objective problem, where the number of objective is more than one, they have applied the particle swarm optimization and shown that the performance is better in comparison to other optimization algorithm. Other optimization in this particular group is artificial bee colony, ant colony optimization. It is also a very famous one. Shuffled frog leaping algorithm, firefly algorithm, glowworm swarm optimizations. So these methods are also very popular methods, but they are belongs to the swarm intelligence group. Like if you go for particle optimization algorithm optimization, we talked about the particles, the behavior of the particles, how they are searching the food in the sky. So based upon that, they have understood their uh, behavior and they have modeled it in the form of mathematical equation. Similarly, if you go for ant colony optimization, we are observing the behavior of an ant, right? And its pheromone, how they are finding the foods and how they are finding a particular path. That things are modeled in the form of a mathematical equations, right? Similarly, if you go for other nature-inspired algorithms, so more or less these optimization algorithms are the recent development in the area of soft computing. Especially, you can see a very famous algorithm under this category is called as a teaching learning based optimization. So in teaching learning based optimization, the main motivation behind this optimization is our classroom teaching, right? In classroom teaching, what happened? Like now I am taking this lecture, around 60 participants has already joined this session. So they are listening to me, right? So it is, you can say 1 to M, right? The M participants are there and there is only one speaker. So that is the teaching page. But when you go for learning phase, after this, let's say this program is over, then one participant may discuss the concept with another participant, right? So that is called as a learning phase. First phase, we learn the thing from a teacher. Second phase, whatever we have learned, that we have discussed. So based upon that, we have teaching learning based optimization algorithm. And an advancement over the teaching learning based optimization algorithm is called as Joya algorithm. Like if you see the teaching learning based optimization, the first phase is teaching, Second phase is learning. So you have to see two different mathematical equations. But when you go for Jaya algorithm, both equations are combined into a single equation. So through a single equation, you can iterate this particular algorithm. So Jaya algorithm is also a very famous algorithm after TLBO. And in fact, a TLBO is a very popular algorithm in nowadays. It is applied in various fields. And recently in 2020, during COVID time, a new set of algorithm, which is, you can say, the background of these algorithms are also TLBO and Jaya. So three variants of algorithm is proposed by Professor Rao from SBNIT Surat. So these algorithms are called as Rao 1 algorithm, Rao 2 algorithm, and Rao 3 algorithms. Right? Not only these algorithms, there are a lot of algorithms belongs to this category. Like simulated annealing is quite old, but a very famous algorithm. Harmony search, charge system algorithm, central force optimization, cross entropy, cuckoo search, grenade explosion method, and biogeography based optimizations. These all are belongs to other nature inspired algorithm. So in this faculty development program, I will talk about genetic algorithm and teaching learning based optimization, Jaya algorithm, and RAW 1, RAW 2, RAW 3 algorithm with its implementation details. I'll do the coding for teaching learning based optimization, and I'll request you to implement the Jaya algorithm because it is a two-phase algorithm and it is a one-phase algorithm. If you understood how we can code for two different phases, you can simply code for one phase. Similarly, in RAW 1, RAW 2, RAW 3 algorithm, I'll implement RAW 1 algorithm and I request you to implement RAW 2 and RAW 3 algorithm. So more or less these algorithms are similar. Once you implement one algorithm, you can implement the rest of the algorithms. Okay, but these implementations I will show you in MATLAB. That's why I request you to install MATLAB. It is not restricted to any particular version. Whatever version you have, that is fine. So try to install the MATLAB or ask someone for MATLAB and install in your system. And if you want to do the coding with me, better you can use two different systems. You can attend the lecture from, let's say, mobile, and you can write the code in your laptop. So in this way, you can simultaneously learn and see the coding also or do the coding also. If not, I'll share the code with you as well as the slides so that you can practice whenever you are free to do that one. So now we'll focus on the first category. Like I mentioned in the evolutionary algorithm, we have genetic algorithm, right? So we'll start with the genetic algorithm and the details related to the genetic algorithm. So the concept of evolutionary computing, it is not new. It was introduced by I. Reichenbach in the year of 1960. So imagine this evolutionary computing is nowadays applied in various domains: civil engineering, mechanical engineering, electrical engineering, computer science engineering, metallurgy. All peoples are nowadays applying evolutionary computing. But the concept is quite old. You can say 60 to 65 years back, this concept was coined by I. Reichenbach. Subsequently, genetic algorithm was introduced by John Holland in the year of 1975. He is affiliated to University of Michigan. So he has given only basic of the genetic algorithm. But nowadays you can see there are several variants of the genetic algorithm. For example, if a particular algorithm is having 5 different steps and you want to modify one of the steps, so that is considered as a variant of the genetic algorithm. So today we have several variants of the genetic algorithm. Right? Now, as a part of an application, as you know that civil engineering is one of the oldest engineering branch. So first application was in the field of structural engineering, which belongs to civil engineering, by two authors. One is called as Goldberg and another one is called as Samtani. Okay, so they applied genetic algorithm in their problem, that is in the field of structural engineering, in 1986. So that is the first applications. So you can see it is around, you can say it is around 36 years back or 37 years back. And after that, it was applied to various fields, and especially as a computer science faculty, I can say you, it has applied to all the fields of computer science engineering. That is, wireless sensor network, cloud computing, vehicle aid-up network, software engineering, irrespective of the field, irrespective of the branch. Nowadays, people apply the genetic algorithm. But you can also do a variance of genetic algorithm. If somebody has applied genetic algorithm in your field, that does not mean that you cannot apply genetic algorithm in your field. You have to see what is the process followed by that particular author. You have to see what variants you can do in order to improve the result of your problem. Okay, then you can compare with the previous one with your one. So there are different variants are there, right? Different improvements you can do. You can also contribute to each and every phase of the genetic algorithm. In that way, you can say your variant of genetic algorithm is better than whatever there in the literature. Now, if you come to any kind of optimization method, irrespective of the algorithm, not limited to genetic algorithm, you will find an objective function. Another word you will find in my lecture, that is called as fitness function. So objective function and fitness function both are different, but it can be same also for a particular problem. But interchangeably using objective function and fitness function, okay, it is wrong, right? You cannot use interchangeably. But for a particular problem, you can consider same equation as a objective function, same equation as a fitness function. So what is our objective function? Objective function may be the standard deviation. Like if I take a data set like 2, 3, 4, 5, 6. Suppose I have taken 5 different values. If I ask you what is the standard deviation, you can calculate, right? You can find mean, then you can go for standard deviation, and you can say this is the standard deviation. So standard deviation can be considered as an objective function. Mean can be considered as an objective function. Or in your respective area, whatever functions you want to minimize or you want to maximize, that can be considered as an objective function. So as an objective function, what is our objective? Our objective is to either minimize that particular function or maximize that particular function. For example, if I consider a function related to time, okay, a function related to time. So our objective is to minimize the time, because if you minimize the time, that will be provide you better result, right? Or if you minimize the time, you can save your time. So time case, your objective is to minimize. Suppose I'll take my objective function is profit, then our objective is to maximize. So in your respective problem, if you want to apply optimization method, first you have to decide whether your objective is to minimize or your objective is to maximize. Now you may raise a question here. In your respective problem, if you have more than one objective, it may happen you want to minimize the time, you want to maximize the profit, right? You have more than one objective also. So in that case, it is better to take a linear combination which balances both minimization as well as maximization. Or you can convert a maximization problem to the minimization problem. On the other hand, you can convert a minimization problem to a maximization problem, take their linear combination in order to solve that particular problem. We'll discuss this thing in the upcoming slide. Now, let us consider a set. Suppose I am taking a set A. Set A consists of some elements. For example, set A consists of x1, x2, x3, x4, and so on, right? So, for example, if I ask you, find an element xo, find an element xo may be x1, it may be x2, it may be x3, it may be x4, or it may be anything. You have to find that such that f of x0 is less than f of x. For example, if I take a set 1, 2, 3, 4, 5, and I have taken a function f which is nothing but whatever input you will give, it will square the output, right? For example, if I take f of 1, if I take f of 1, then the output is 1 square. If I give f of 2, then it will give 2 square. Similarly, if my highest element is 5, if I give, then it will return me 5 square. So, if you find f of x0 which is less than equal to all the elements that are present in the set A, then you can say it is a minimization problem. For example, if you see in this case, if I take f of 1, f of 1 is less than equal to f of anything in that particular set. You take f of 1 also, it is less than equal to. You take f of 2, it is less than. You take f of 3 here, it is less than. F of 4, it is also less than. So we can say this is a minimization problem. So for minimization, for all x, it should be belongs to A, this condition should be satisfied, right? Like in this case, you can see if I take a square is the function, then 1 is the value which is minimum or among all the elements that is given in the set A. On the contrary, if you go for a maximization problem, what you have to do, f of x is less than is equal to f of x0. So f of x means, suppose I will take an element, let's say f of 5, right? F of 5 will give you the highest one. If there are 5 elements in the set, 5 square is 25, and that is the highest one. All other values, you take value as 1 or 2x1 or x2 or x3 or x4, even if x5 also, that value is less than is equal to f of 5. So what we can say, it is a maximization problem because it for all x belongs to A, this particular condition is satisfied, right? So in this way, you have to specify a minimization problem or a maximization problem. Now, if you are talking about the genetic algorithm, there are some important discussions, right? First one is, in order to represent your problem in genetic algorithm, first you need a set of variables, right? So how these variables in genetic algorithms are encoded? The very first phase of genetic algorithm is called as encoding. Suppose you are dealing with a particular problem for which, let us take, you have a set of works. Let it be work 1, work 2, work 3, work 4. These 4 works you have to assign to 2 different computer systems or 2 different machines, which we call as M1 and M2. Okay. So if you go for encoding, okay, if I go for encoding, so my encoding size is just having 4 different locations. What these 4 different locations is that, for example, I am writing 1, 2, 1, 1. What it actually indicates? It indicates, the first one indicates that the work 1 should be given to machine 1. What 2 indicates? 2 indicates that work 2 should be given to machine number 2. And what this one indicates? It indicates that work 3 should be assigned to machine 1 and work 4 need to be assigned to machine 1. So if you have a set of works that you want to assign to 2 different machines, you can model your you can model your chromosome, or you can perform the encoding by taking a 4 different cells, right? So first you have to see how you can model your problem into a chromosome, or you have to perform the encoding. That is the very first phase you have to do if you want to apply genetic algorithm in your respective domain. Next important part is you have to see how fitness function is calculated. In the previous slide, we have discussed about objective function. Okay, we have discussed about objective function. Now we are discussing about fitness function. So in this slide, you will understand what is the difference. For example, this is one of the solution. I can say solution 1. Similarly, another solution is, it may be 2, 1, 2, 2. It is also another solution. Another solution may be, you can say 1, 1, 1 and 1. That is also another solution. So there may be different type of solutions you have. So how to know which solution is better? In order to know that, you have to check their fitness value. Okay, if fitness of this particular one solution is better, then you can say out of these three, the best fitness value we found in the solution number 2. But what objective function is giving? Objective function is giving whether the value is a minimized value or that value is a maximized value. So you have to know how the fitness function is going to be calculated. Now in genetic algorithm, we have a phase that is called as selection phase. What we want to do in the selection phase, the different types of methods are there through which you have to choose the best solutions. Suppose I have given you 10 solutions, okay, and I'll ask you choose the best 4 solution. Like in the campus placement case, if you see campus placement case, a lot of students appear for the exam, written exam, but finally you have to select, let's say 10% of the student or 20% of the student. So how you will do it? You will conduct a test or you will conduct an interview. These are nothing but various selection methods. So some of the popular selection method that we are going to discuss in this lecture, that is called as roulette wheel selection. Second one is Boltzmann selection. Third one is called as tournament selection. Fourth one is called as steady state selection. A lot many methods are there to select some solutions out of a group of solutions. So you can apply any method to solve to find the best solutions out of all the possible solutions. The next one will discuss about the population of the mating pool. How to make the reproductions, right? Like if I take 2 different chromosome, I will make the crossover. Like if you see there is a male chromosome and female chromosome, if we do crossover, then you can see there is a child, right? In the similar process, here also we are going to take 2 different chromosome. We will choose a crossover point, and through that crossover point, we are going to generate 2 different children. So we'll see that how this reproduction process happens. Next one is about the inheritance operator. That is nothing but which you want to apply to the mating pool. So not only there is a single chromosome, there is a group of chromosome is there. So you have to apply some operator. Okay, there are lot many operators are there, like crossover, mutation, lot many operators are there to update the mating pool in each and every iteration. So basically these things we will discuss in this complete lecture. Now, coming to some of the very important questions related to any type of optimization algorithm. First question arises is that, does an optimal solution exist? Suppose a problem is given to you. If I ask you, is there any optimal solution to that particular problem? Right? Like if you go for a mathematical quadratic equation, I'll ask you to find the value of x. Then you can find the value. If the quadratic equation means 2 values of x you will find, right? First you have to determine for your problem for which you want to apply genetic algorithm, does any optimal solution exist for that particular problem or not? Okay, now if there is an optimal solution exists, Now the question arises, is that solution is a unique solution or not? It may not be unique also. Like in mathematics, we have seen there are various ways to solve the problem, right? A number of ways to solve the problem. It may not be unique also, right? So you should know whether it is a unique solution or there are multiple solutions exist for a particular problem. Then you should ask what is the procedure to get the unique solution or the optimal solution. And the next two questions is related to if we are going to change some parameter, like you have tuned a particular model using some parameter. If I slightly change a particular parameter, how sensitive the optimal solution is? Is it going to affect the optimal solution or not? On the other hand, how the solution behaves for small changes in parameter. You have applied in one particular scenario of your research problem. You want to apply another scenario of your research problem. So if you compare these two scenario, what is the difference? There is a small change in some parameter. Okay, so you should know that whether your model performs as expected or not. That's why you need to know how sensitive your solution is. Now, when you deal with a large space, you cannot apply genetic algorithm in each and every possible case. Genetic algorithm should be applied if your problem is you are whatever you are solving, it is in a very large source space. That's why genetic algorithms are good at taking larger, potentially huge source space and navigating them, looking for optimal combination of things and solution which you may not find in your lifetime. One of the example I'll tell you. For example, if you consider 512 different tasks and 16 different machines. Okay. If you consider 512 different tasks and 16 different machines. If I ask you how many possible solutions you can generate by taking any arbitrary sequence, right? For example, as there are 16 machines are there, first task you can assign to first machine, second task you can assign to second machine, third task to let's say fourth machine. Okay, like that you have to assign 512 number of tasks to some machine. Okay, out of these 16 machines. So how many ways you are going to distribute these 512 tasks to 16 machine? Can anybody tell? How many ways you can distribute these 512 tasks to 16 machines?
C5.
16C5. 5 or 512? 16C?
So 5, because we have to distribute 5 tasks in 16 machines.
No. I have taken, madam, 512 different tasks.
Okay, 512. Okay.
Yeah. So if you see, you will find it is 16 to the power 512. Okay. That many possible solutions are there. Okay. So 16 to the power 512 number of possible solutions are there. So obviously 16 to the power 512 it is difficult to calculate. So I'll give a more simple calculation. It is much greater than 10 to the power 512, right? And 10 to the power 512 means 1 followed by 512 number of zeros you have. So imagine if a particular solution, so this many solutions, and if you see the number of solutions, it is more than this 1 followed by 512 number of zeros, right? This is set for easy illustration or easy discussion. I have taken 10 to the power 512. So if you go for each and every solutions, right? Suppose for per solution it is 1 millisecond. Okay, your computer will take 1 millisecond to test one particular solution. So it will assign 512 different tasks to 16 different machines, and it will see how much time it is taking. Then it will choose the second solution. First solution it is tried, then it will go for second solution, which also take 1 millisecond. Let's say third solution, fourth solution, up to you have to go for 1 followed by 512 number of zero solutions. So if you see this particular problem, if you calculate how much time is required to solve this 10 to the power 512 number of solutions, you will not find the solution in your lifetime. Right? In such a cases where your source space is very large, you can apply the genetic algorithm. Another example I'll also tell you, like if you consider a electronics gate, right? In electronics gate, you have to give two input. This is your input one, okay, and this is your input two. And once you provide two input one, input two, you will get your output, right? So as it is binary, right? We represent it in binary. So input one and input two may be 0 0, or it may be 0 1, or it may be 1 0, or maybe 1 1. So based upon this input, you will get your output based on what kind of logic you have used or what kind of gate you have used. Now see how many possible combinations you have here. There are four different possibilities, right? But here, how many possibilities we have seen? We have seen 10 to the power 512 possibility. Actually, it is 16 to the power 512, but we have taken 10 to the power 512 or easy calculation, right? So for this case, we have only four possible cases. So in that case, you should not apply the genetic algorithm because your source space is very small. If source space is very large, then only you have to apply genetic algorithm. Otherwise, you should not consider genetic algorithm as a part of solution. As because others are applying genetic algorithm, you should not apply genetic algorithm to your particular research problem. Right? Now, there are three most important aspects of the genetic algorithm. First one we have already discussed, that is called as objective function. Second one is called as genetic representation, which we also call as encoding, right? Or chromosome representation. How you can represent a particular problem in the form of a chromosome. I'll solve another problem also. Third one is what kind of operators you want to apply in the genetic algorithm. Not only whatever operators we know, like if you aware of genetic algorithm, we apply two operator. One is called as crossover, another is called as mutation. But apart from crossover and mutation, there are a number of operators are there. Like if you see, there are several low-level operators are also there. If you go for traditional genetic algorithm, you will see number of operators are applied to genetic algorithm. Like you can see inversion, dominance, deletion, intrachromosomal duplication, translocation, segregation, speciation, migration, sharing, mating. These all are related to different inheritance operator. Is there any question, anyone? If you have any question, you can unmute and ask. Okay, so there are three very famous basic operators we are using in genetic algorithm. I already told you about crossover and mutation. Another operator is called as reproductions. So most of these operators I'll discuss in much detail in the upcoming slide. Now, this is your flow chart of our genetic algorithm. Just you can take a snapshot of this particular picture so that while I'm discussing in the upcoming slides, you can see where we are, right? So the first one is called as initial population. So in initial population phase, first one is you have to perform chromosome representation or you have to do encoding, right? Like I told you, four different works are there, W1, W2, W3, W4. These you want to assign to two different machines, M1 and M2. So the chromosome representation is four cells, right? First one represent the work one, second one represent work two, third is work three, work four. Suppose you assign work one to first machine and work two to second machine, work three to the first machine and work two to the second machine. So this is a solution. Whether this solution is going to give you good result or that we don't know, but this is a solution. This is a valid solution. But if I write 1, 2, 1, 3, is it a valid solution? 1, 2, 1, 3. Can anybody answer? 1, 2, 1, 3. Is it a valid solution for this particular problem? No, right? Obviously it is not. Why? Because here you can see there are third machines, right? There is no third machine. Okay, if third machine is there, then you can take 3. This is called as this is producing an invalid solution, right? So sometimes in order to avoid this one, we apply the process of genetic correction. Okay, because all are random variables, right? So sometimes while writing code also you may commit mistake. Sometimes by mistake also, or intentionally or unintentionally, you sometimes commit mistake. In order to avoid that, you have to make the genetic corrections. So in initial population, suppose you want to take only, let's say, 30 to 40 chromosomes, right? This is one of the example of one chromosome. This is another chromosome. So you have to take 30 to 40 valid chromosome, right? Then you may ask, sir, why it is 30 to 40, why not 100, right? So there is no standard rule that how many initial population you are going to select. So different articles says different thing. Okay, there is no you can say clear cut method that how many populations you should take. Okay, let us take 40. Okay, let us take 40 different initial population. And once initial population is done, right? So you have to make the selection. So before performing selection, you have to check that what is the fitness of these 40 population, right? Like 1 to 1 2 is better, or 1 to 1 1 is better, or 2 to 1 2 is better, or 2 1 2 1 is better. The number of possibilities are there. So out of these 40 possibilities, right? If I take 40, so you have to see out of 40 populations, you have to evaluate the fitness of all the population before applying the process of selection. And in the process of selection, what you will do, out of these 40, you have to select the population which are performing better. Okay, and those who are not performing, that is replaced by the population which are performing better. Like in a campus interview process, suppose 40 students appeared, right? You have applied a selection process and you found that let's say 20 students are better. Okay, whatever your criteria is there, the criteria is satisfied by 20 people, and rest 20 people, what you will do, you have to discard them, right? But in the process of genetic algorithm, what it says, you have to select 20 only, right? But you have to take a duplicate copy of this 20 chromosome, right? So 20 plus 20, but 20 plus 20, it is again 40. But this 40 is not same as this 40, because here you have discarded 20 bad performing chromosome, and you have replaced with another 20 chromosome which are performing better. Like these 20 chromosomes are performing better, so you have done replication or duplication. Okay, so after that we reach to the process of new population, and the process of genetic algorithm actually iterates from new population. Okay, so after taking 40 population in the new population, we call them this 40 population as parent. Okay, these 40 populations are called as parents. Then we first check that the terminate condition. Terminate, what do you mean by terminate condition? You can say this particular loop, you can see there is a loop here, right? This process, then this process, then this process, again this process, then again you have to back to new population. So this particular loop, you have to do how many times? Maybe 20 times, maybe 40 times. That you have to put as a termination condition. Sometimes you can say that, suppose I am considering standard deviation is my termination criteria. So I'll say until unless the standard deviation is less than equal to 0.5, you have to iterate. Once you get below 0.5, I am satisfied with the solution. So such type of conditions you have to put here. So if the terminate condition is satisfied, then you will stop. If the terminate condition is not satisfied, then you are allowed to do the iteration. So while you are doing iteration, the very first phase is called as crossover. Okay, so crossover is always done with the parent. How many parents we have? We have 40 parents. Out of these 40 parents, you randomly choose two parents. Okay. Randomly you choose two parent. Then you have to perform crossover. I'll tell you detail about these steps in the upcoming slide. So I'm just briefing the steps, whatever there in the genetic algorithm. So you have to take two parent. You have to perform crossover. So suppose you are taking parent 1, parent 2, and you are performing crossover. So the output of crossover is called as children. Children means you will get child 1, you will get child 2. Right? Now, this child 1 and child 2 is given input to mutation. Note that mutation always performed for the children, not for the parent. Okay, sometimes while implementing this genetic algorithm, we misunderstood that mutation is applied to the parent, but that is not true. Mutation is always applied to the children. So after applying mutation, let's say you got modified children 1 and modified children 2. Right? You got modified children 1 and modified children 2. Right? So modified children 1, modified children 2 is after performing the mutation, which we call as modified children. If you make some modification in the children, we call that as a modified children 1, modified children 2. And the process to modify is called as mutation. Now we are checking the fitness. Fitness is checked between whom? Parent to the modified children. Okay, we'll check whether parent 1 is performing better or modified children 1 is performing better. Okay, then we'll see whether parent 2 is performing better or modified children 2 is performing better. Right? So like that, once you compare parent 1, parent 2, modified children 1, modified children 2, suppose you feel that modified children 1 is better and then parent 2 is better. So parent 2 is already there in the this parent pool, right? Only this modified children 1 is to be inserted into this parent pool by replacing parent P1. Okay. So while checking the fitness, if you found that modified children 1 and parent 2 is better, then parent 2 is already there in the new population. So only the modified children 1 you need to insert into the new population by replacing P1. So at any point of time in your new population contains 40 parents only. Right? Like that, we'll iterate a number of steps and we'll stop a particular point where our termination condition is satisfied. Is it okay? Or if you have any question, you can ask.
Excuse me, sir. I have a doubt.
Yeah.
How
Yeah,
do we set the terminate condition? Like in order to achieve the optimum condition, so
yeah.
priorly only you are setting the termination condition, right? So how do we know
Yes.
that at this point only we will achieve optimum solution? How do we decide that?
You have to take one function, okay, let's say objective function, right? Initially you cannot say that whether objective function is below 10 or below 5 or below 6, right? After carefully observing your problem only you can decide a particular criteria. That's why most of the soft computing techniques consider that after 20 iteration or 40 iteration, whatever result we are getting, we'll consider that result as final result.
Okay.
Okay, we do not have any specific criteria to stop the algorithm. Like I told you, you can set standard deviation is below 0.5, then only you will stop, right? But there is no such termination condition for most of the problems. That is the reason most of the research articles, they consider 20 iteration or 40 iteration. After that, whatever result you are getting for these 40 parents, and the best result is considered as your near optimal solution. So in any soft computing techniques or this optimization method, you will get the value which is close to the optimal solution. Suppose that your optimal solution is 2, right? So you will get the solution as 1.998. You may get a 2.001, 1.996. So such type of solutions you will find. You will never find the result is 2. Okay, that we are expecting. Yeah.
And one more thing, sir, like you
Yeah.
have said that we duplicate the data by neglecting who are
yeah,
not
exactly.
performing well and adding some other 20 contestants like who are
Yes,
performing well, right?
yes,
But
yes.
we considered only 40 population. We haven't considered 60. So how do we choose that another 20? From where do we get them?
I'll show you, madam, one example. I'll show you what actually I told you. Out of 40, let's say 20 populations are performing bad, good, and 20 is performing bad. So we delete these chromosomes and we make a duplicate of these 20, right? So
So
this
what
20 again,
exactly do you mean by duplication, sir, here?
I'll show you an example in the
Okay.
upcoming slide. Okay.
Okay.
And if it is still not clear at the end of the lecture, you may raise the same question again.
Sure.
Yeah. Okay, now coming to creation of offsprings or sort space, as I said, the space for all possible feasible solution is called a sort space. Like I have taken 16 different machines and 512 different tasks. So my sort space consists of 16 to the power 512 number of solutions, right? This is called as all possible solution. You will not find any solution beyond this 16 to the power 512. That is called as my sort space. But doing this 16 to the power 512 is very, very difficult for me. That's why instead of taking 16 to the power 512, let me take only 100 solutions, right? If you go to 16 to the power 512, definitely you will get your optimal solutions. But with 100 population, if I get near optimal solution, then I can say my approach works, right? Although I am not getting, let's say the value is optimal value is 2, with 100 if I am getting 1.9, then also it is acceptable, right? Because this you will not get in your lifetime. For that, each solution can be marked with a fitness value. Suppose I am taking 100 fitness, 100 different population. For each population or each solution, we have a fitness value, right? Like I have taken a set A, I have taken 5 elements, 1, 2, 3, 4, 5. Okay. If I take the first value, my fitness value is 1. Second value, let's say square. Square means it is 4. Third value, 3 square is 9. This is 16. This is 25. These are nothing but the fitness value. Now, looking for a particular solution, our objective is to look for a solution. That means looking for an extreme. Either your objective is to go for the maximization or your objective is to go for minimization. That's why I told you maximization case we are taking this one, minimization case we are taking this one. So this sort space, like if you go for 16 to the power 512, this is very, very complicated and we do not know where to look the solution. That's why we have applied the genetic algorithm for such type of problem. Now, let us take a small example to understand what we discussed till now. So let us consider a maximization problem. Let's say your problem you have modeled as f of x. F of x may be x square minus 2x plus 5, something like this. So our objective is to maximize f of x. And this value of this particular x is within the limit of xil to xiu. This is the lower limit and this is the upper limit. N stands for lower limit, u stands for upper limit. Like we sometimes say that x value lies in the range of -2 to +2. Right? Now, suppose you are given with a maximization problem. If I ask you, convert it into a minimization problem. Like I told you, one particular problem P has two objectives. One is objective 1, another is objective 2. Objective 1 is to minimize, objective 2 is maximize. So what you have to do? If you convert this minimization problem into maximization problem, then your objective is both objective is to maximize. That's why if you want to minimize f of x, where f of x is greater than 0, so you can say converting this minimization to maximization problem by doing 1 by 1 plus f of x. So minimizing f of x is same as maximizing 1 by f of x. But as f of x may be equal to 0, we have added an extra one here. Right? You can write 1 by f of x, there is no problem. But you have to ensure that f of x is greater than 0. Right? If f of x is equal to strictly equal to 0, then this will be 1 by 0. So in order to avoid that, we have written 1 by 1 plus f of x. Now, if f of x is less than equal to 0, it may also possible the value is negative. In that case, you have to maximize minus of f of x, right? So in this way, you have to convert one problem into another problem to solve a problem using genetic algorithm. Another very popular problem, that is called as a NAPSA problem. If you are not belongs to CS background, the NAPSA problem is a problem where suppose you want to go to a shopping mall, right? You have carry bags with you, right? And you have to carry vegetables or some goods and something, some items from the shopping mall, right? So you are given with the values and size. Let's say item 1, the value is 1 kg and the price is 100 rupees. Item 2, let's say the weight is 500 gram and the price is 70 rupees. Like that, you are given with a set of items with their values and size. Okay, and the bags, whatever you have to carry to the shopping mall, that bag is also having a capacity. You cannot keep as much as possible, right? There is a limitation, right? We cannot exceed that one, right? For example, in that shopping mall, for a simplicity of example, we consider there are 12 different items available in that shopping mall. So if I ask you represent it in the form of chromosome, then you will say you take 12 different cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So this is starting from item 1, item 2, item 3 up to item 12. So what you can do? You can say if you carry a particular item, you represent it by 1. If you don't want to carry a particular item, you can put 0. And subjected to the maximum capacity of your knapsack. You cannot exceed that capacity. So one of the solution you can see, I have picked item 1, item 3, item 4, and so on. That is one of the chromosome. Another chromosome, I selected item 2, item 5, item 6, and let's say item 9 and 10, right? That is also one of the valid chromosome. So in this way, you can represent a particular problem into a particular problem in the form of a chromosome representation, and this process is called as encoding. So here the encoding, whatever we have used, that is called as a binary encoding, because you have represented in the form of 0 and 1. 0 indicates you don't want to carry that item. 1 indicates that you want to carry that particular item. Now, not only that, you can also represent different items in the form of different codings. You can go for octal, you can go for hexadecimal, any type of requirement is there, you can fulfill by doing that one. Like here you can see, suppose I have taken a 2 variable function. One variable is x1 and x2, and each and every variable may be representing one particular item. X1 is an item, x2 is another item, and I am representing each and every item by a 4-bit number, right? 4-bit binary means it is 0, 0, 0, 0, 2. It will continue up to 1, 1, 1, 1, right? So if I ask you what is the range of x1 and x2, you will say it may be 0, 0, 0, 0 to 1, 1, 1, 1. It may be also 0, 0, 0, 0 to 1, 1, 1, 1. So this is my lower limit and this is my upper limit. This way you can represent. Suppose you feel that 4-bit is not sufficient, then you go for 5-digit. That is also possible. And for example, there are total item is 15. Okay, so if I go for 4-bit, then it is 2 to the power 4. So you will get 16 codes starting from 4 zeros to 4 1. Right? If you go for 2 to the power 5, then if there are 32 items in your shopping mall, then you can represent it from 4 zeros to 4 1. Like that you can represent. But not necessary. These values are in the range of 0 to 15, or this is 0 to 31. 32 items means we represent by 0 to 31. 16 items means 0 to 15. So if it is not there in that limit, you can use this particular formula to convert the scale from one range to another range. So writing 0 to 15 is same as writing 2 to 17. Both are same only. Here also you use a 4-bit. Here also you use a 4-bit string to represent the item, right? So you can take the lower limit, okay, upper limit minus lower limit, and 2 to the power 4 minus 1, okay, multiplied by decimal. So you will get the value is 12 for the case 1010. But 1010 is, if you see it, it is in binary. If you convert it into decimal, it is nothing but 10. Okay, it is nothing but 10. But in the, if you go to the scale of 2 to 17, then you will get the value is 12 in the decimal, right? So it is also not necessary to code all the variables in equal substring length, what we have seen here, right? Now see another one. Here if you take this particular problem where I have taken 1 to 16, instead of taking 0 to 15, I have taken 1 to 16. What is 1? 1 represent 40, 2 represent 0001, like that you will go for 4 ones. And their decoded values are 0, 1, 2 up to 15. So 0 indicates the angle, the fiber angle is 0. 1 indicates the fiber angle is 10. So the difference between these two is 10, right or not? 10 to 20, the difference is again 10. 20 to 30, difference is 10. 30 to 45, the distance is 15. 45 to 16, 60, the distance is 15. 60 to 70, the distance is 10. So while you are converting a particular problem and represent it in the form of binary string, you need not follow the same pattern. Like you can see somewhere the distance is 10, somewhere the distance is 15. If you see, there is a huge distance here, 90 and minus 10, huge distance is there. So it is not necessary that they are equally distributed, nor it is not necessary to take the equal string length while you want to do mapping for your problem to in the form of binary or any type of coding scheme. It is not necessary to follow that one. Now you can see here I have taken octal 0 to 4095. So octal means the values are in the range of 0 to 7, 8 values. Similarly, you can take the values in the range of 0 to 65,535. Okay, that is nothing but 0 to 9, then A to F, A, B, C, D, E, F, right? So total 16 values are there. That's why you call it hexadecimal. So most of the research articles, wherever you will see, they simply use the decimal representation or they use binary representation. But nobody give details about the octal representation and hexadecimal representation. Although the representation is same only. Whether you do in octal, hexadecimal, the process is same, right? But if you represent octal and hexadecimal, the size of the chromosome will reduce, right? The type of the problem will look simpler. So in your problem also you can do that one. Another type of problem is called as a traveling salesman problem, which is also very popular problem in computer science and mathematics. So traveling sales problem, what you have, suppose there are 9 different cities are there. 1, 2, randomly I'm taking 3, 4, 5, 6, 7, 8, and 9. So a salesperson is there. The salesperson has to visit all the 9 cities in any order. Okay, I may follow 1, 2, then let's say city 8, then city 7, city 6, city 5, any order. Finally you have to reach to city number 1 again. Okay, you have to make a round, visit all the 9 cities, but each and every city need to be visit only once. You should not visit the same city twice. So for this particular problem, if I ask you to represent in the form of chromosome, then you will say first we have started with the, let's say first you started with 1, then you visited to 5. I'm following this one, 1 to 5, then 5 to 3, then 3 to 2, right? 2 to 4, right? 4 to 7, 7 to 9, okay, 9 to 8, 8 to 6, then 6 to again 1. So it is a valid one. Each and every city is visited only once, right? Like that, if you go for chromosome B, 8, 5, 6, 7, 2, 3, 1, 4, 9, that is also a valid one. 1 is there, 2 is there, 3 is there, 4 is there, 5, 6, 7, 8, 9, all the cities are there. So there is no issue. But if a city is repeated, suppose instead of city 9, let's say city 8 is there. What it indicates? The city 8 is repeated twice and city 9 is not repeated. So in that case, what we are doing? We are doing genetic operator correction. We need to correct it. Okay, because this is an invalid chromosome. This is not a valid chromosome because the same city is digitted twice. Similarly, whenever you are solving a particular problem, as there is a randomness in the randomness is there, so you may find difficulties. So you have to solve that problem by making genetic correction. Now there is another problem also you can see, like many research problems are there in which you want to represent your chromosome by taking decimal number or floating point number or a double number. Like you can see here 1.234, 5.32. These are nothing but the floating point numbers or double numbers or decimal numbers. Okay, so these in this way also you can represent your chromosome, right? For example, if I say neural network weight, okay, neural network weight, right? Like in neural network, you have a input layer, you have a output layer. In between input and output, you have set of hidden layers. So there, if you consider the weight is generally looks like this particular number, these numbers. So in that case also, you can use genetic algorithm, represent in the form of a chromosome. Similarly, you can take A, B, D set of alphabets that can be also used to represent the chromosome. Or if you talk about a robot, the robot action may be forward, backward, left, right, such type of actions you can give to the robot. That is also considered as a chromosome. You can represent such action in the form of chromosome. Similarly, many people also represent the chromosome in the form of a tree. Okay, they have taken functions and commands. Like sometimes we use prefix notation, sometimes we use postfix notations to represent it. For example, x plus 5 divided by y. You know, division has more priority than the addition. So if you do prefix, then it is division 5 and y. Then if you make it with x plus, it is nothing but plus x. So this is the representation. So in this way, what you can do set of codings. Not necessarily always you go for binary coding. Based on your problem, based upon your suitability, you can represent in the form of any type of coding. Now, initially, the genetic algorithms are used for solving the maximization problem. Okay, they targeted for maximization problem. So if minimization problem is there, they are transferred into maximization problem. I also told you, right, if there is a minimization problem, you can do it by taking 1 divided by f of x. You can do so if f of x is not is equal to 0. But if you assume that f of x is equal to 0, then it is better to add a plus 1 in the denominator to avoid that particular problem. Now let us see a particular problem in which you will understand whatever we discussed till now. So here I have taken an objective function. The objective function f is nothing but pi of theta 1 and theta 2. So theta 1, theta 2 are two different angles. Okay, theta 1 is angle, theta 2 is angle. That will be given as a input to you. Then you can calculate it minus 4 sine theta 1, minus 6 cos theta 1, minus 4 sine theta 2, and minus 2 cos theta 2. And the range of theta 1 and theta 2 in the range of 0 to 90. Right? So now if I represent, you know, the angles are in between 0 to 90. So if you want to go for 4-digit binary, so maximum you can represent 15 or 16. So if I divide by 15, okay, then I'll get 6 degree. Okay, what it indicates? First code is 0000, it represents 0. So 0001 represents the degree 6. Similarly, 0010 represents degree 12. 0011 represents degree 18, right? That's why in each and every code difference, you will find the difference in the degree is 6. Right? Now, see this particular problem. This is the coding, whatever you've done, right? You can see 4 zeros represent 0, 001 represents 6, 12, 18, 24, up to 19. Okay, 4, 1 indicates it is 19. Now, this is called as your objective function. Note down, this one is called as your objective function. But here I have taken another function that is called as fitness function. So the fitness function f is equal to f dash minus 7. Here fitness function is different than your objective function. What is f dash? F is nothing but your objective function. So fitness function is equal to objective function dash minus 7. Right? So what is objective function? The objective function f you have seen as minus 4 sine theta 1, minus 6 cos theta 1, minus 4 sine theta 2, and minus 2 cos theta 2. Right? So if I put this f value here, and let's say f dash is nothing but minus of f and minus 7. F dash I have represented as minus f. So minus f minus 7. Yeah, any question? Anyone?
Okay, sir. Sir,
Yeah,
what
madam.
is the logic of taking the fitness function as minus 7 extra than the objective function?
No, I have randomly taken, madam. There is no answer to your question. I have randomly chosen this as minus f minus 7.
Okay.
There is no logic behind it. Just to tell you how we are solving a particular problem using genetic algorithm.
Okay, thank you, sir.
Yeah, madam. So now, see, this is minus f minus 7. You know f value is this one. So I can write f is equal to minus of minus 4 sine theta 1, minus 6 cos theta 1, minus 4 sine theta 2, minus 2 cos theta 2. Right, and minus 7. This is my fitness function. So what I did here, in my initial population, I have taken randomly 8 different population. If you remember, while discussing the flow chart, I told you, you take 40 population, you take 20 population. So you can take, there is no standard rules to select 10, 20, 40 or something like that. So here we have taken randomly 8 different population. So the population means what? Suppose I have taken 8 zeros. What 8 zeros indicates? 8 zero indicates first 4 represents the angle theta 1. Okay, so it is 0. Next 4 represents theta 2, which is equal to 0. Right? Next is, if I write 0, 0, 1, 0, you can go back to this slide. You tell me what is the equivalent angle of 0, 0, 1, 0. It is 12, right? So you can see theta 1 value is here 12. And 0, 0, 0, 1 means it is 6. Now let us go to population number 5. 0, 1, 1, 0 and 1, 0, 1, 0. 0, 1, 1, 0, which what is the angle? 0, 1, 1, 0. 36, right or not? Then another I told you, this is 36. 1, 0, 1, 0. 1, 0, 1, 0 means 1, 0, 1, 0. Where is 1, 0? Yes, it is angle is 60. So randomly you have taken some population, that is 8 population, and you know each and every population is 8-bit, right? And their corresponding angle is written here. Now you tell me, if you choose one particular population, can you calculate what is the fitness value f? Can you calculate or not? You can calculate, right? If I put theta 1 value is 0, this theta 1 value is 0 for first population, theta 1 is 0, theta 2 is also 0, theta 2 is also 0. Solve it. You will get minus sine 0 means what? Sine 0 is 0, right? Sine 0 is 0, cos 0 is 1. Okay. So sine 0 is 0 means the entire term is 0. Cos 0 is 1 means it is minus 6. Sine 0 means again 0, right? So this cos 0 means it is 1, so it is minus 2, right? And minus 7 is there. So minus, this is minus 6 and minus 2, minus 8, right? But there is a outer minus is there. So it is 8 minus 7, so you will get 1. So the fitness value you got here, it is 1. Yes. Rachit Verma madam also mentioned that one. So population 2, you can also solve population 2 by putting theta 1 value is 12. This theta 1 value you have to take 12 and theta 2 value you have to take 6. Then you will get the fitness value is 2.10. Now I think it is clear. You are calculating the fitness value for each and every population. Okay. And if it is a maximization problem, tell me which population is better. If it is a maximization problem, maximum problem means maximum value is always better. So which population is better? Can anybody tell? Yes, population number 5, because it is giving you the fitness value as 4.66. 4.55 is the next best one, right? That is population number 8. In this way, you can decide which population is good, which population is bad. So yeah, for this particular problem, if you see population 1 is performing very bad, right? Its the value is 1, which is lowest among all, right? So yes, here you can find the difference. The objective function is the function to be optimized. Okay, this is your objective function, right? But fitness function is what it is doing. It is guiding the optimization. Now by looking into this fitness value, you can decide which one is good, which one is bad. So it is guiding you the process of optimization. But objective function, you have to achieve that particular part, right? That you have to optimize, whether to minimize it or to maximize it. Okay, now come to one particular phase that is called as reproduction or selection operator. So it is the first operator that we have applied to the population. So what we are going to do here, those population which is above average, they are picked as current population. I told you there are 3 type of population you will find. One is good population. Okay, one is average population, and there is bad population. So here it says that above average strings are picked for current population, and above average populations will make multiple copies. Okay, and they are inserted into mating pool. But bad populations we have to discard. So I'll show you an example. The idea will be more clear. So for this, we have the process of selection. If you remember in flowchart, we have initial population. Now initial population is done. You have taken 8 different population here. Then the process is called a selection. If you have taken snapshot of that flowchart, you can see now we are in the phase of selection. Numerous methods are there for selection. One by one, we'll discuss. Start with the first method, that is called as Roulette-Hill selection. Right? What you are going to do in Roulette-Hill selection, you know this particular column, you know this particular column, you know this particular column, you know this particular column. Okay, in initial population phase, I have explained what is this column. Only the new thing here is this particular one. So what Roulette-Hill selection is doing, a string is selected from the mating pool with a probability proportion to the fitness. So after finding the fitness of each and every population, we are finding average fitness. Okay, what is average fitness? Average fitness is nothing but sum of all the fitness divided by 8, because we have taken 8 population. So sum of all fitness value divided by 8, you will get 2.908. That is the average value. So you can see those values which are below 2.908, they are bad population. If it is above 2.908, they are above average population. So now, in order to calculate the probability of each and every population, so we have 8 population. Assume that 8 different candidates are there. They are appearing for campus placement interview. So you have to decide which student is having more probability to get that interview. Okay, for that, what we are doing, this cumulative value is 23.27, that we have divided in each and every population. Like here population value is 1, I have divided by 23.27. So I got 0.0429. Come to the last one. What is the fitness value? 4.55. I have divided it by 23.27. That is nothing but sum of all population. Sum of the fitness value of all population. So I got the value as 0.1955. Right? That means it is something called 4.29%. It is called as something 19.55% or equivalent to 5%, equivalent to 20%. So you can say population 8 is having 20% probability, or candidate 5, candidate 8 is having 20% probability. But what about candidate 1? Candidate 1 is having only 5% probability. Right? Is it clear up to this? This PI value is clear? Or any question in PI? Please unmute and tell, or you write in the chat box. Yes. If it is clear to you, then what you have to do, you is the name for that, it is called as a roulette wheel. Okay, you have to make a wheel, right? So this is a wheel, right? So we have 8 population. I told you first population takes 5%. So you have to give 5% space to the population 1. But what about population 8? Population 8 you told 20%. So here you can see population 8 is given 20%. Right? Like each and every population has some space in this roulette wheel. Now what you can do, there is a marker in the wheel. Right? There is a marker in the wheel. So if you spin this wheel, if you rotate this wheel, after some time it is going to point to a particular population. Right or not? If I spin, definitely it will reach after some time to in a particular, by pointing to a particular population. So that population is going to be selected. But you tell me, if a particular population occupies maximum area, like here it occupies 20%, here it occupies only 5%. So definitely more probability is there for population 8, or more probability is there for population 5, because they occupy more areas, right? That's why the 5th individual and 8th individual also is having higher fitness. So they have more chance to select in this particular roulette wheel selection procedure. Now, see how actually this procedure works. So we have calculated the cumulative probability, right? Cumulative probability is nothing but you have to see the probability of first one. When you are calculating the cumulative probability for the second one, you have to add the probability of the previous one and the current one, right? For example, see this one. Now up to this, I think it is clear up to this, right? Now we'll go for column A. Column A is calculated in roulette wheel selection by multiplying it with 8. You know the probability of first population is 0.0429. If you multiply with 8, then you will get that value is 0.33. Similarly, if you take 0.2 and multiply with 8, you will get 1.6. Okay, what is the reason of calculating this? I will tell you, right? Now, B column represent the cumulative probability. So cumulative probability of the first one is always the same, 0.29. If you want to find the cumulative probability of the second one, which is nothing but 0.0429 plus 0.0900. If you calculate the cumulative probability of the third one, it is nothing but 0.0429 plus 0.0900 plus 0.1336. So in this way, you can generate the column number B. Right? Now, if you go for cumulative probability, after calculating cumulative probability, you come to column number C. Column number C contains the random number in the range of 0 to 1. Any number. These values are random number generated using any function. Like if you go for MATLAB, while discussing the implementation part, I'll show you in MATLAB there is a function called RAND. So if you type this function, it will generate the values in the range of 0 to 1. It may be any value, right? Now, interesting thing, you can see the column D and E. Like I told you, those fitness which are above average, that you have to select and make multiple copies. Those fitness is below average, that you have to discard. How this selection is done in roulette wheel, let us see. Now come to D. D column says that suppose the value is 0.259 here. How you got this value? This value is a random value. Now you tell me 0.259. You go to column number B. Column number B is nothing but your cumulative probability. You tell me where 0.259 will lie if you go for column B. Is it in the range of 0 to 0.0429? The answer is no. Is it between 0.0429 to 0.1329? Again, no. Is it between 0.1329 to 0.266? Check. It is in the range of this one. So the value is written here is 3. Okay. Now you tell me 0.038. Is it in the range of this one? 0.038. Yes, that's why it is written as 1. Similarly, 0.428. Is it in the range of this one? 428. This is 0.0428. So it is no. This is also no. This is also no. Is it between 0.266 to 0.438? The answer is yes. That's why the value is written here. It is 4. Right? Now, once you have prepared the column D, column E is counting how many times 1 is there, how many times 2 is there, how many times 3 is there. So see, 1 is here, so it is writing 1 time. 2 is here, 1 time. 3 is here, so 1 time. 4 is here as well as here, so it is 2 time. 5 is here and here, so it is 2 time. 8 is there 1 time. But there is no number with the 6 and 7. That's why we consider the 6 and 7 is the 6 and 7 is called as your, just a minute. So you can see 6th and 7th population is not there, right? So you have to discard the population 6 and 7 from your mating pool, and you have to take multiple copies of what? 4 and 5. You can see multiple copies of 4 and 5 because their frequency is 2. Why it happens? Because if you look into cumulative probability, more space is occupied by population 4 and 5, right? Or you can say out of all the population in comparison to other population, you got maximum space occupied by these population. Maybe other also occupy the maximum space, but in this calculation, we got 4 and 5. That's why they are repeated twice, okay? And population 6, 7 is discarded. Is it okay? Have you understood this one? Or if you have any question, you can ask.
Hello.
Yes, sir, please.
So thank you very much for your explained lecture. Actually, this is Mustafa
Yeah.
Shamim Firdaus, a Commonwealth
Yeah,
scholar.
yes, sir, please. Yeah.
Sir, my humble request to you is that
Yeah.
this genetic algorithm, I mean, it's a very integral part of today's, I mean, modern day research and applied kind of work. So it would be
Yeah.
very kind of you if you please be kind to suggest me some very good books on this particular thing so that I can study further and I can be connected
Yeah.
with you through email to actually know much more about it. Thank you very much, sir.
Yeah. Yeah. So there is a book in my reference section. The book name is Neural Network, Fuzzy Logic and Genetic Algorithm, Synthesis and Application. I'll save the slide with you, sir. It is with the PHI Learning Private Limited publisher. So you can refer that book for more details about genetic algorithm. I'll save the slide. You will find the first reference. Yeah.
Thank
Yeah.
you.
Thank you very much. Okay. So I hope it is clear, roulette-hill selection. But the problem with the roulette-hill selection is that there is two issues with respect to this one. One is called as population diversity. Another is called as selective pressure. So what population diversity says, so sometimes we are favoring good individuals and we are discarding those who are not good individuals, right? So we are thinking that picking the good individuals is a benefit for us to find the solution in much better way. But sometimes also it faces, you will face sometimes a problem. Similarly, if you perform high selective pressure, the convergence rate is higher. Okay, if you put low selective pressure, then definitely the convergence rate is slow. So you have to decide, you have to make a proper trade-off, right? What you have to apply to avoid this type of problem. Okay, quickly I'll tell you other different methods. There is second selection method that is called as tournament selection, right? So let us consider 8 different populations and their fitness value, right? I consider 8 different populations with their fitness value. Now, randomly, I'll choose 2 different individuals. Is the name suggests tournament. I'll make a tournament. They will play a match. In each and every match, there is a winner and there is a loser. Suppose there is a match between 2 and 4. So the fitness of 2 is 2.10. The fitness of 4 is 4.01. Let us assume that this is a maximization problem. If it is a maximization problem, 4.01 is the winner, 2.10 is the loser, right? Suppose there is a match between 3 and 8. 3's fitness value is 3.11. 8 fitness value is 4.55. So 4.55 is the winner, 3.11 is the loser. Similarly, if I take another one like 2, 4, this is not 1, 3, this is 2 and 4. So 1 and 3 only, sorry. This is 1 and 3, so it is Q1 and this is Q3. So one population is one's fitness value is 1, 3's fitness value is 3.11. So 3.11 is the winner and 1.0 is the loser. So if you do such type of tournaments, you will see that who is winning maximum matches. Those populations are winning maximum matches, they are above average. Those populations are winning less, okay, or they are losing more, they are below average. So we have to discard the populations that are below average and we have to accept the population which is above average. Okay, like that here you can see, if you go for roulette wheel selection, we have omitted 6 and 7. But if you go for tournament selection, we have noticed that 1 and 7 are not chosen at all. However, if you see 4 and 8, they won 2 matches. 2, 3, 5, 6, they won 1 match each, right? That's why we have discarded 1 and 7 and we have made duplicate copy of 4 and 8. Okay, I'll take another copy of 4, I'll place here. I'll make another copy of 8, I'll place here. That's why I told you, initial population, if I have initial population case, if I have 8 different population, after the process of selection also, I will get the value is 8 only. But the difference is that the 8 population, whatever you have in this initial population, it may not be same as this 8. Okay, maybe it is the duplicate of 4. Okay, maybe 4 copies, 4 populations are above average. I have taken 2 copies each, right? So in this way, tournament selection is different from the roulette selection. Now proceed to the next selection method, that is called as rank selection. It is a very important selection method. Like you can see this particular wheel where the population 5 is occupying 75% space of the circle, right? So definitely when you spin, okay, when you spin, the most chance is that the population 5 is going to come, which is possible in the case of roulette wheel selection, and that is the main drawbacks of roulette wheel selection. So in order to avoid that, what we are doing, we are going for a rank selection. For example, population number 5 is occupying more space, right? That is 75%. And population 4 is 10%, population 3 is 8%, population 2 is 5 and 2. So we assign the rank. Okay, so those population are occupying more space will give the highest rank to them. Highest rank means 5, not 1. And those in the population which occupies less space, that will give a rank 1. So sum of these ranks, if you calculate 1 plus 2 plus 3 plus 4 plus 5, you will get sum of the rank is 15. So now if you calculate the percentage, this is the sum of rank. Your rank divided by sum of the rank. That will give you the percentage, like 1 by 15, this is 2 by 15, like that it is 5 by 15. So whatever percentage you will get by using that percent, if you draw the wheel, if you give the space in the wheel. So it is much better presentation in comparison to the previous one. Like you see here 5 is dominating all, but here, although 5 is having more space, but it is not like the previous case. That's why rank selection method has a better result in comparison to better performance in result to the relative selection. There is another method that is called as elitism. So here the best and few best chromosomes are copied to new population. Those we have seen also in the previous cases. So it was proposed by Goldberg in 1989, right? And he suggested that the fitness of any ith individual must be subtracted from a large constant. So suppose you are calculating the fitness values, assume that your fitness values are positive. So I have taken a very large number, let's say 5 lines. And if I subtract all the fitness value from this one, then the value is positive only. So fitness value is always non-negative. And if there is a minimization problem, you can use fmax minus fmin minus of fix, right? This is the fitness value, and you have to choose the maximum value and minimum value. If you subtract it, then you will get the value of phi I. And if fi is positive for the maximization problem, then phi I can be equal to fi. So this is another method. So let us see one example for it. So let us consider same 8 population. So you know these are the 8 different populations we have taken, and this is nothing but the phi value which we have calculated. That is nothing but the fitness value, right? First value fitness we have calculated as 1. Now I am calculating f bar. F bar is nothing but average fitness. Average fitness is coming as 2.908. You sum all the values divided by 8, you will get 2.908. Now if I do f divided by f bar, that is 1 divided by 2.908, 2.10 divided by this, you will get this particular column. Now what you will do, you have to find the highest value, right? I told you in the previous slide, we need to find f max, we have to calculate f min. So which population are you having highest value? Population 5. Next best is population 8. And worst one, if you see, one is the worst one, that is 0.38, and second worst one is 0.738. So we have to discard the population number 6, population number 1, and you have to keep multiple copies of population 5 and population 8. Okay, that's why it says that this method, worst fit individuals are die off, and mating pools is created where individual 1-6 is die off. And in order to compensate the population 1 and 6, we have taken multiple copies of 5 and 8, right? There is another concept related to genetic algorithm which is called a generation gap. Like our parent generation, grandparent generation, what is the change in these different generations? So in order to calculate the generation gap, you can use this particular formula, that is GP is equal to P divided by NP, where NP is the population size and P is the number of individuals. Suppose you have 10 different population. Out of 10 different population, 5 populations are replaced in this generation. So you can say it is 0.5. Okay, 0.5 means 50% of the population is replaced in this generation. Let's say in the next generation you got 2 divided by 10, so you can say 20% populations are replaced. Okay, so you can apply various schemes to do this one. Like you can select the parent based upon the fitness. Like I told you in the flowchart, there is a column that there is a diamond which says that check fitness. In check fitness, what you are doing? You are comparing the fitness of the previous generation with current generation. So in that case, you can select the parent based upon the fitness, and replacement can be done random. Or the first one may be random, second one is based on the fitness or inverse fitness. Or both can be at random, or both can be at fitness or inverse of the fitness. Such type of schemes we have to apply in order to update our population. So the next operator that is applied in genetic algorithm, that is called as crossover. Now we reach to initial population. Initial population, we have checked the termination condition. If termination condition is not satisfied, then we have to make the crossover. Crossover means crossover should be applied to the parent. So if you perform crossover, so you have to find a crossover point. Let's say crossover point is 2. First, you have to choose 2 different population and a crossover point. So let's say crossover point is here. So this is one population. This is another population. Let's say the crossover point is here. Then the children is going to take the first part of this one, second part of this one. Similarly, another children can take the first part of this one and second part of this one. So this A star and B star are the 2 children of 2 parent. One is A, another is B. Okay, and the type of crossover what we did here, that is called as single point crossover. So this is also an example of single site crossover. We have selected 2 different parent and a crossover point, and the first part I have taken from parent 1, second part from parent 2, which is my child 1. Similarly, I have taken the first part of parent 2, second part of parent 1, which I call as child 2. That is called as your single point crossover. Similarly, you can go for 2 point crossover. So in 2 point crossover, you will choose 2 parent, but number of cross sites is more than 1. Right here, 2 point means it is 2 points you will take. One is called as cross site 1, another is called as cross site 2. So you will take, in order to generate child 1, you will take first part of parent 1, second part of parent 2, third part of parent 1. Similarly, in order to go for child 2, you will take first part of parent 1, parent 2, second part of parent 1, third part of parent 2. So these are this is an example of your 2 point crossover. Not only that, you can go for multi-point crossover also. Right, like here you can see there are 2 cases of multi-point crossover. Like if I take a ring, okay, if I take a ring has no start point and no end point. Okay, that is called as even number of cross sites. Right, for example, if I choose these are the cross site points. Okay, so I'll take the first part of the parent 1, second part of parent 2, third part from parent 1, fourth part from parent 2. Right, this is same as your child 1, and the reverse one, okay, opposite one is called as your child 2. Similarly, you can apply odd number of cross sites if you know where to start. So here we assume that the start is here, starting point is here. So I have taken 3 different cross site 1, cross site 2, cross site 3. So these are the 2 different parent. I am taking the first part of parent 1, second part of parent 2, third part of parent 1, fourth part of parent 2. So one after another, if you choose, that is called as the crossover. Similarly, there is other crossovers methods are there, like one is called as uniform crossover. In uniform crossover, what we are doing actually, each bit is either taken from the first parent or the second parent with a probability of 0.5. Like you can see here, child 1 is taking from the parent 1. Once this I is encountered, okay, some marker is encountered, it is going to take from parent 2. Right? It is going to take from parent 2. Once another I is detected, it is going to take from, okay, like here it is going to take from parent 1 only. Here I means it is going to take from parent 2. Okay. So either parent 1 or parent 2 based upon the probability 0.5. Similarly, there is another example of uniform crossover. In this uniform crossover, we have taken a crossover mask. In crossover marks, 1 indicates that there is 2 values, 1 and 0. 1 means you will take from parent 1. 0 means you will take from parent 2. So you see here, offspring 1. Offspring 1 means your child 1. Child 1 is taking, is the crossover mask is 1, it is taking from parent 1. Crossover mask is 0, so it is going to take from parent 2. Crossover mask is 0, so it is to take from parent 2. Like that, you can generate offspring 1. And in the reverse way, if I take 0, here I have taken 1 is parent 1, 0 is parent 2. If I do the reverse one, 1 is parent 2, 0 is parent 1, then I can generate the offspring too. Okay, in this way you can perform the uniform crossover. Similarly, many people are working in image, right? Image processing, right? Or computer vision application. In such application, you can apply matrix crossover. So, you know, matrix is a set of rows and columns, right? So a set of rows are there and set of columns are there. So you can choose one element from parent one or another element from parent two, either in the row order or column order. So that parent one, parent two, it looks like this one. Then child one, child two will look like this one. There is another concept related to the crossover that is called as crossover rate. Crossover rates as say that it is the ratio between number of pairs to be crossed divided by fixed population. For example, if you have taken 100 population and you want to make crossover of 50 different populations. 50 different populations means you will take 50 pairs. So 50 divided by 100. So again, it is coming as 0.5. So we call that as the value 0.5 is called as crossover rate. So it is suggested that the crossover rate should be 0.5 to 1. That means you can go for 100% crossover, but it should not be below 50% crossover, right? That means if I take 8 population, in our example we have taken 8, so minimum number of crossover we have to do is 4. Okay, in order to achieve it is 50%. Okay, so this is the example. If 50% are you have performed crossover, rest 50% you have to take as it is. So these populations are not going to be changed. It may be changed in the upcoming iterations. Like that you have to perform. There are some other operators are there apart from crossover and mutation, right? One operator is called as inversion. What inversion says? Inversion says that you have to choose 2 cross site, okay, 2 random sites, and you have to flip the bit. That means 1 is converted to 0 and 0 is changed to 1. So that operator is called as inversion. But now if you see in the recent variants, we are not using the process of inversion. Why I am telling this one? Because when you go for your respective research domain, you may find such type of problem. Okay, there is another called as deletion. You have to choose 2 cross sites, okay, and you have to delete the bits. Okay, I have deleted this bit, and I may, what I can do, I have to copy this 10. I have copied to here. I deleted 2 bit and copied the previous 2 bit as my next 2 bit. Right? That is called as deletion. Similarly, there is another process that is called deletion followed by regeneration. I have deleted all the bits from these 2 cross site and I have regenerated it. I have not followed the previous one or after whatever the values are there, but I have simply deleted it and I have regenerated it with the new values. Similarly, there is another approach is called as segregation. Okay, segregation says that the bits of the parents are segregated, then crossed over to produce the offsprings. Like here you can see I have taken a part of parent 1 and the same part appear in the child 2. I have taken some part in the parent 2, it appears in the child 1. It is also same as our single point crossover. You choose this particular point and generate the children. But as we are focusing on one of the part of the chromosome, we call this process as a segregation. The next one is called as crossover and inversion, right? So I have taken parent 1 and parent 2. First, what I have to do? I have to make a crossover. Crossover means this part, let's say this particular part and this part. I will take one parent 1. Then first part, second part, and third part I will take as parent 2. So you will find these 2. This is called as your child 1, child 2. Then the process is called as inversion. Inversion means this part you will take and you will flip it. Flip it means you will get 0, 0, 1, 1. Similarly, you will take this part 0, 1, 1, 0 and you will flip it. That means you will get 1, 0, 0, 1. So this process is called as you have to make crossover. After making crossover, you have to make inversion. Right? But irrespective of this operator, the main problem with genetic algorithm is that, like if I take this population This is population 1, population 2, population 3, and population 4. You do whatever crossover we have learned. We have learned uniform crossover, 1-point crossover, 2-point crossover, multi-point crossover, matrix crossover, deletion, segregation, inversion, regeneration. Whatever operation you want to apply, you will see the first bit will never change to 1. Okay, if first bit of all the parents is 1, then it will never change to, if first bit is 0, then it will never change to 1. Okay, that is the main problem in the crossover. So in order to avoid that, we are performing a step that is called as mutation. So what actually we are doing in mutation, like I have selected a particular bit and I have flipped that bit. If the bit is 1 here, I have flipped that bit to 0. Okay. Similarly, I have selected this particular value. I have changed this value as to minus 67.5. Okay. So like that, how many mutation you can do? Crossover case, I told you 0.5 to 1 crossover you can do. But in mutation case, you can do 0.001 to 0.5. So with a population of 8, maximum you can do it is 4. Although it is recommended as 30 to 200 population size, but generally you can go up to 50% mutation. Okay, the maximum mutation is 50%, but maximum crossover is 100%, right? Now, there are some other operators that you can apply that you know, bitwise operators. Like 1's complement operator means 0 is converted to 1, 1 is converted to 0. And there is a bitwise AND operator which says that if both bits are 1, then only the child is 1. In rest of the cases, whether it is 0, 1, 1, 0 or 0, 0, the bit values are 0 only. Similarly, we have bitwise exclusive OR. Exclusive OR operator. Exclusive OR operator says that if both bits are same, then the output is 0. If there is a difference in the bit, then the output is 1. These operators also you can apply if it is applicable to your domain. It is required whenever you are applying the genetic algorithm. Similarly, other operators, bitwise OR operators, OR says that if both bits are 0, then only it is 0. Other cases, it is 1. Or you can apply left shift, right shift operator. Right, left shift operator, you will move towards the left, right? Like here you can see this 0 is now moved to this one. If I shift to 2 bit, 1 is here, 1 is here, and rest bits is padded with 0. Similarly, right shift operator, this 1 is here, this 0 is here, 0 is here, and these 2 bits are padded with 0. So this is called as a left shift, right shift operator you can apply. Now let us summarize whatever we have discussed with another problem. Suppose there is another problem given to you in which, let's say, the objective function is nothing but the number of ones. In your population, you have to find how many ones are there. Like if I consider 4 different populations, P1, P2, P3, P4, first population case, the number of 1 is 3. Out of 10 bits, so the fitness is 0.3. Last population case, how many ones are there? 5, 6, 7, 8, 9 out of 10. So the fitness value is 0.9. Okay. So if I calculate average, without looking into average also, you can say this is underperforming, right? This is overperforming. What I have to do? I have to discard this P1. I have to take multiple copies of P4. This is also called as your dominant theory of survival, which says that strongest individual has 2 copies. Strongest individual is your P4. Average individuals have 1 copy, that is P2 and P3. And weakest individual, which is P1, they have 0 copy. Right? Now, what you have to do, once it is done, you have to make crossover. If there are 4 populations are there, you can do at minimum 2 crossover, right? So see how many crossovers we are doing. Here we are doing the crossover with 1 and 4. I'll take this first population, 4th population. I'll make crossover at 0.1 and 5. That means it is a 2-point crossover. This is 0.1, this is 0.5. 1 point and 5 point. So if you do crossover, you will get, this is the crossover value. See here. Now I'm taking the first part of this one, second part from this one. Okay. Then third part from this one. You will get this one. Right. Similarly, if you choose first part here, second part here, third part from here, you will get this one. Now you can see the fitness is improved to 1.0. That means all values are 1. Here the fitness is equal to 0.5. Now crossover is done, but you have to go for mutation. So mutation, suppose we are doing 6th bit of string 2. 6th bit of string 2 is this one, and first bit of string 1 is this one, right? So 2 out of 40 bits are muted here, right? We have taken 2 out of 40 bits. So it is mutation probability 0.5. So you can see this 1 bit is changed to 0 here. This 0 bit, it is changed to 1. So after doing this one, if you see the fitness is improved to this fitness. Okay, see this fitness. Earlier this fitness is 0.1. Now it is degraded to 0.9. That means parent is better. But if you look into this particular case and this one, okay, in this case, children is better than the parent, right? Like that, you have to make the complete generation, this particular case, in order to get updated mating pool for the next iteration. So this process you have to iterate multiple times, not only one time. You have to make 20 and 30 times in order to accept any result. Okay. So this is the complete picture of genetic algorithm which we have discussed. And I told you about this particular book. You can refer if you want. This book is a nice book for genetic algorithm. In fact, the slides are prepared based upon this particular book. And if you want a research article, you can refer this particular research article for genetic algorithm, right? But it is in the field of wireless sensor network. If you are little bit knowledge of wireless sensor network, you can understand it more clearly. Okay. Okay, thank you everyone. If you have any questions, you can ask. Yeah, somebody's asked about the best journal, right? Best journal of genetic algorithm. Yes, the best journal is, you can say, Swarm Evolutionary Computing is published under Elsevier. It is a very popular journal. Soft Computing Springer is also having good papers related to not only genetic algorithm, any optimization methods that you can refer. Any other question, anyone? Okay, many people have asked about attendance. So there is no attendance system. Okay, you attend the lecture as per your convenience. I'll save the recordings. Yeah, once the recordings is generated, I'll do it. I'll share with you. But Google also takes 3-4 hours to generate the recordings. So most probably next day, means tomorrow daytime, I'll share the recordings in view mode, not in the download mode. But it will be there for forever, right? Yeah, any question? Arun sir, have you asked any question? Okay, any more question? Can you explain again how copies are made in Darwin method? Darwin method says that the best individual, suppose I have taken 4 different population. Out of 4 population, the best population is copied twice, and the worst population is deleted. And average population means 2 population will be there if it is 4. So that will be considered only one time. So that is called as Darwin method of theory, survival of theory. Okay, thank you, Rachita madam. Rachit Verma.
Thank you, sir. Sir, at what time next session will start?
Next session will start at 5:15. Madam is already there, but as I am late by 9 minutes, I'm sorry for that, and we'll start the next session at 5:15. Yeah, thank you everyone. If you have no more question, we'll start the next session at 5:15. Thank you, everyone.
Hello, am I audible?
Yes, ma'am.
Once again, good afternoon to all of you. Again, I welcome all of you to the first day of our program sponsored by ELICT NIT Warangal, organized by Department of CSC, NIT Warangal. So in the first session, Dr. Sanjay has discussed about different traditional optimization algorithms. He has given a brief introduction about different optimization algorithms, and he explained the genetic algorithm, what are the steps you have to follow in order to solve the problem by using genetic algorithm. Right? So in this session, I am going to discuss another two algorithms. One is simulated annealing algorithm, and another is an ant colony optimization algorithm. So we'll see some of the applications or some of the problems, how these problems can be solved by using simulated annealing algorithm or ant colony optimization algorithm. If time permits, I will show you some data in Python in my class. So let me share my screen. Is my PPT visible?
Yes, madam, visible, madam.
Right. So first I will talk about the simulated annealing algorithm and we'll solve two problems. One is the job sequencing problem and another traveling cells person problem. Then in the second part, we are going to talk about this ant colony optimization.
Ma'am, your voice is not clear.
Not clear?
The sound is rebounding, madam.
Rebounding.
Yes, madam.
Just one minute. Is it okay now?
Yeah, ma'am. Now it's clear.
Okay. Yes, my PPT is visible. Hello.
Yes, ma'am. It is visible.
And now voice is audible?
Yes, ma'am. Audible.
Oh, okay. Right. So let us start this simulated annealing algorithm, how this algorithm works and what are the applications of this simulated annealing algorithm. Right? So I told you we are going to discuss about this application of simulated annealing algorithm to solve the job sequencing problem and to solve the traveling salesperson problem, right? And whatever Dr. Sanjay has solved that problem, right? That problem also we can solve using the simulated annealing algorithm. So in the genetic algorithm, you have seen, right? Always you are trying to choose the best population or the best chromosome for the next iteration, right? So always we are trying to move towards the best. But in the simulated annealing algorithm, there is a chance that we can accept the inferior solution also, right? So whichever solutions are not good, we may choose some of the solutions so that after doing a certain number of iterations, we may reach towards the best solution or the optimum solution. Right? So generally, simulated annealing algorithm, this is a probabilistic technique for approximating the global optimum of a given function, right? So this is a stochastic algorithm, that means some randomness is there, right? So some random numbers we are using to take some decision at every stage. And this is the peculiar property of the simulated annealing algorithm. It escapes from the local optima by allowing some of the inferior moves, right? So all the inferior moves we are not selecting here. So we are applying some probability, right? Some acceptance probability we are getting, and depending upon that acceptance probability value, we are trying to accept an inferior solution also for the next iteration. So when this simulated annealing algorithm, or what type of problems we can apply the simulated annealing algorithm? For the problems where finding an approximate global optimum is more important than finding a precise local optimum, but in a fixed amount of time. In that scenario, simulated annealing may be preferable to find out the solution. Right? So generally, this simulated annealing algorithm, this is motivated by the physical annealing process that you have studied in the physics, right? In the school level, you have studied. Right? So that will see how this physical annealing is mapping as an optimization problem through this simulated annealing algorithm. So coming to the history of simulated annealing algorithm, so Metropolis et al. They in 1953. This is very old algorithm, but nowadays, right, researchers they are combining different types of optimization algorithms to find out the best solution. So the numerical simulation of annealing, this was proposed by Metropolis et al. In 1953. Then the same simulated annealing algorithm, Kirkpatrick, they have used to solve the combinatorial problems. That means the combination of solutions they have found by using the simulated annealing algorithm. Right? So if you see this diagram, suppose, right, if you there is a ball here, right, this is the initial position of the ball, and we are trying to find out, right, the point at which the position is minimum, right. If you see in this diagram, so this is the point where we are getting the best solution, right. So if you apply the greedy algorithm to solve the problem, I hope some of you have known the greedy algorithm. So this greedy algorithm, it works in stages. At each stage, you are selecting one input at a time, right? So always you are trying to find out the best solution at each stage, right? So here, suppose you apply some greedy algorithm, you may stuck here, right? That means the ball may be able to reach up to this point, right? So because in this direction there is no better solution, always there is the right highest point peak is there. Right? So this is the disadvantage of this greedy algorithm, where we may stop at a local optimum problem because we are able to see this is a minimum point available, right? So if you apply the simulated annealing algorithm, what happens? There is a chance that, right, this side your inferior solutions are there, this left side also inferior solutions are there. Right? So there is a chance that you may move towards the inferior solution, and if you repeat or if you iterate for a number of times, this algorithm it may converge towards this global optimum solution. Right? So what is our target here? We are not getting any best solution out of from this point. So we are trying to accept some of the inferior solution, right? And that how to accept that inferior solution, for that some probability calculation we have to do, and by using that probability value we are going to move in the direction, right? So at a later stage, upon a large number of iteration, there is a chance, right? So always you will not get the global optimum solution. There is a chance that it may converge towards this global optimum solution. So this is the basic difference between your simulated annealing algorithm and the greedy algorithm. So as I told you, so the problem where your global optimum is required, right? Those type of problems, right? You can apply this simulated annealing algorithm. So basically, this is inspired by the physical annealing process, and you can solve the large combinatorial optimization problems by using the simulated annealing algorithm. So these are the some of the basic applications: your traveling salesman problem, graph partitioning, assignment problem, job sequencing. So there are other problems, right, related to your particular domain, problem domain or the research domain. There may have some optimization problems. So if you can see whether you can solve that optimization problem with respect to your domain by using this simulated annealing algorithm. So in this session, I am going to discuss about this traveling salesman problem and the job sequencing problem. How to solve this problem by using simulated annealing. Right? So now we'll see how to map this physical annealing or the real annealing with the simulated annealing. Right? So as you know, in the physical annealing, what happens? We have to increase the temperature of the metal with a high temperature. So what happens? The molecular structure of the metal will change. Right? So in order to restore the original property of the metal, what we have to do? We have to decrease the temperature very slowly. Okay? If you decrease the temperature very slowly at a particular point of time, the particles they may arrange themselves in the ground state of the solid. So that is the physical annealing process. Okay? So it has two steps. As I told, increasing temperature. You have to increase the temperature of the metal or the heat bath to a maximum value at which the solid melt, the molecular structure will change. Then you have to decrease the temperature very slowly so that the molecular structure will restore. So the same concept, right? Same concept we are trying to mimic through an optimization problem, and that optimization technique is called a simulated annealing. So here in the first column, if you see, these are the some of the property of the physical system, and the second column, we will try, right, the concepts, basic terminology of the optimization problem. So the system state, whatever your molecular structure, we are talking about the metal, right? The molecular structure is changing with respect to temperature. That structure, or the molecular structure, or the system state, we can call that is a solution, right? Molecular positions, those are called your decision variables. The values of the variables we want to optimize. And the energy, right? The energy level will change with respect to your temperature for the metal. So that energy is called an objective function. And our target is to minimize the energy, so that is the minimizing the cost. So we can solve the maximization problem also. Right? And the ground state means what is the original molecular structure of the metal, that is your global optimum solution. So what happens if you decrease the temperature very slowly, right? You may reach towards the original molecular structure, but you may not reach the original molecular structure also. So that is the ground state is called the global optimum solution. And the metastable state, where the molecular structure is not exactly same as the original structure, right? So those are called the local optimum. And here the temperature we are increasing and the temperature we are decreasing also, right? So the temperature is the control parameter in the optimization problem. So with respect to this temperature T, the solution space will change for the optimization problem. So in that way, we are mapping this physical annealing or the real annealing to the simulated annealing algorithm. So how this algorithm works? So now if you see, there are different terms with respect to optimization problem. Your control parameter T is there, right? What is the global optimum? What is the local optimum? How to define the objective function, right? How to choose the inferior solutions, and how to whether to accept the inferior solution or you have to reject the inferior solution. So those things we have to see how this the working procedure of the simulated annealing algorithm. So the flowchart, this is the flowchart of simulated annealing algorithm, right? So this is also very simple, right? So you can initialize the solution and the temperature. As we have seen in the genetic algorithm, right? We are having a population size. So this is, we are not using here population, we are initialize the solution, single solution we are considering. And from that single point, we are trying to move towards the optimum solution. So this is not a population-based algorithm, right? This is the single point where the single solution we are considering at a time. So what you have to do? Initially, you have to initialize the solution and the control parameter, that is the T, right? Then what you have to do? You have to generate a random neighbor solution. Again, how to generate the random neighbor solution? That depends upon the problem, which problem you are solving, right? So for that purpose, we'll see the job sequencing problem and the TSP, how to find out the neighboring solution, right? Once you have generated, right? So what you have to do? You have to apply a neighbor function to the initial solution to find out the neighbor solution set. And from that set, you can choose a randomly solution, right? One solution you have to select from the neighbor set. Now you have to compare whatever neighboring solution you are selecting randomly, right? Is this a better solution than the initial solution? If that is yes, right? Suppose I want to minimize some function f of x with respect to the variable x. The value of initial solution is x equals to 3. Next step, what I am doing, I am choosing suppose x equals to 5. And the f of x, suppose with respect to 5 is minimum, right? So that is the better solution. So if that is a better solution, I have to accept the neighboring solution, right? So if the better solution, the neighboring solution is better, we have to accept the neighbor solution, right? If the neighboring solution is not better, right, that means that is an inferior solution. That solution is not good compared to the initial solution, right? So here what we are doing, here we are determining whether you have to accept the inferior solution or we have to reject the inferior solution, right? So this is the basic concept in the simulated annealing algorithm. So should we accept the inferior solution? So how to determine yes or no? For that, some acceptance probability function you have to apply and you have to determine the probability of acceptance. If yes, right, that means you are accepting the inferior solution also. If no, what you have to do? We have to update the temperature. So the temperature updating, right, this also follows some annealing schedule. So randomly you cannot update the temperature, right? Some procedure you have to follow to update the temperature. So after updating the temperature, you have to check whether cooling enough. That means the T, control parameter T is there, right? Whether you have reached the minimum value of the temperature, right? If yes, you have to end the solution. You have to end the procedure here. If no, again what you have to do? Again you have to generate a random neighbor and you have to repeat the process, right? So whatever, if the cooling is enough or you are able to reach the minimum value of the temperature, you are terminating the procedure, and whatever solution you are getting here, right, you are accepting the neighboring solution. That solution is an optimum solution for the given problem. This algorithm is very simple, only you have to use here, right, how to find out the acceptance probability of the inferior solution, and depending upon that, how to update the temperature. Some annealing schedule you have to follow, and you have to follow, or you have to follow some mathematical equation to determine the acceptance probability of the inferior solution. Only two mathematical functions we have to use. So what are the terminology that can be used in the simulated annealing algorithm? So first, your basic iterations, how many iterations you have to do, right? And how many steps you have to do. Second one is your neighbors of a state. How to find out the neighboring solution from a given solution, right? Third is how to calculate the acceptance probability of the inferior solution, or this may be the better solution also. How to find out the acceptance probability of the neighboring solution. And the final one, that is the annealing schedule. How to change the temperature, I mean how to decrease the control parameter T, right, in order to terminate the procedure. So these things you have to fix, right? You have to map the given problem. For these things you have to find out how to initialize these things. So how this basic iteration, what happens, as you know, in every meta-heuristic optimization algorithms, there are some computational steps, and you have to repeat those computational steps for a certain number of iterations till your termination criteria is reached. So what you are doing here in the simulated annealing algorithm, the basic iteration is that at each step, the simulated annealing heuristic, it considers some neighboring state S star of the current state S. Right? So assume the current solution is S. In the next state or the next time stamp, we are selecting the neighboring solution as S star. Right? So whether you have to select the S star or you have to reject, accept or reject. So that the probabilistically decides between moving the system to state S star or staying in the state S. If you are rejecting the neighboring solution S star, that means you are staying in this same solution S, right? So how to find out this solution, right? So this probability, it will lead the system to move to the states of lower energy, because you are decreasing the temperature. You are right, you are reducing the control parameter T value by following the annealing schedule. Right? So typically, this step you have to repeat until the system reaches a state that is good enough for the application, or until a given computational budget has been existed, right? So that is your termination criteria you have to fix for your problem, right? So first I told you, right? So initial solution you have to consider, right? Then you have to find out the neighboring set, or you have to apply a function to find out the neighbors of the solution. So your state represents solution of the optimization problem, right? Again, it varies from one problem to another problem, right? Suppose we will see the traveling salesman problem, how to find out the neighboring solution. What we will do, we will permutate the cities to be visited, right? What we will do, we will swap the number of cities, right? Suppose 1, 2, 3, 4, 5, one solution is there. So in between the cities 1, 2, 3, 4, 5, these are the city numbers. So randomly we will swap this city number. So we will get another neighbor, right? So we'll see, we'll solve this TSP by using the essay so that we can understand. So this random or the neighboring function, right, or the neighboring set, it depends upon the problem, which problem you are solving and how to find out the neighbors, right? Okay. Next is your acceptance probability. Right? Once you have determined or you have applied the neighboring solution, neighboring function you have applied to find out a neighboring set, all right, you have to randomly choose one solution from the neighboring set. So whether you have to accept or you have to reject, right? For that one, right, there is a control parameter I told you, that is the temperature, that is the T, right? So initially it starts with a smaller energy, that means higher temperature, right? And even what will happen, the probability function P, it must be positive when the E nu is greater than E. So E nu is the energy value of the neighboring solution and E is the energy value of the current solution. Right? With respect to this E nu and E, in between, if you compare this E and E nu, you can determine whether the neighboring solution is a better solution or this is the inferior solution with respect to the initial solution. So this picture, right, because we are initially we are keeping the temperature as very high, slowly we are decreasing the temperature. So it prevents the method from becoming stuck at a local minimum, which is worse than the lower. Right? So this is the use of this acceptance probability. So how to find out this acceptance probability, right? So what will happen? So as I told this already, I told the algorithm starts initially with T is set to a very high value, then it is decreased at each step following some annealing sequence. But at the end, right, that cooling enough we have seen in the flow chart, right? So what we are checking basically, we are checking T equals to 0. If T equals to 0, that means we are terminating the algorithm there. Right? Now let us see, we'll consider a simple problem, how to solve this problem by using the simulated annealing algorithm. Now see, so suppose there is an optimization problem. You want to maximize or minimize z equals to f of s, small s, where small s belongs to the capital S. This is the solution space, right? So we are having in the essay simulated annealing algorithm, we are having the adjustable of the control parameter T, that is called the temperature. So how the temperature, right, the every iteration, right, the temperature is Ti, I equals to 0, 1 to I. These are the schedule, how to schedule these temperatures. So how the temperature will change? So the each Ti is applied for a specified number of consecutive accept iterations, that is the small t, right? So this small t, suppose small t equals to 2. That means after every 2 accept iterations, I mean after accepting 2 neighboring solutions from the current solutions, we have to change the temperature. This is the annealing schedule. And by how much the temperature has to change, for that you have to find out that value also, right? If S0 is the static solution of the search, right? So how to change the temperature? This Ti is basically the initial value of T0 is, temperature is, there is a random number R0 is generated, which follows the uniform distribution in the range 0 to 1, multiplied by objective value of the S0, right? So with respect to the static solution, what is the objective value? Then you multiply with a random number in the range 0 to 1. You have to set that value as the T, or you can set the temperature T as a very high value, right? There is no hard and fast rule to initialize the value. Right? Then how to change the temperature? As I told, for every small t number of accept iterations, we are going to change the temperature. So Ti equals to, in the current iteration I, this equals to, again you generate a random number Ri. So for every iteration, you are generating the random number which follows the uniform distribution in the range 0 to 1, right? Then multiplied by the temperature in the previous iteration, that is the Ti minus 1. Right? So this is the annealing schedule. This is the initial value of the temperature. Then only one thing is remaining, that is how to find out the acceptance probability. And depending upon the acceptance probability value, how to decide whether you have to accept the neighboring solution or you have to reject the neighboring solution. Right? Assume we have the current solution is Sk or the last accepted solution is Sk. Right? In the next iteration, suppose we are selecting one solution from the neighborhood set. Assume that is the Sk plus 1. Right? So whether we have to accept this Sk plus 1 or we have to reject this Sk plus 1. Right? So if we are rejecting Sk plus 1, that means Sk is the solution only, right? Because we are not changing the solution to Sk plus 1. Right? So how to do this one? If you remember the flowchart, if Sk plus 1 is better than Sk, right? So how to determine if Sk plus 1 is better than Sk? So for that, you have to find out the objective value f with respect to Sk plus 1. Right? If f of Sk plus 1 is better than f of Sk, right? Again, it better means you have to define whether this is a minimization or maximization. Minimization means it should be less and maximization means it should be greater than. Right? So if the objective value of the neighboring solution is better than the initial solution, so what is the probability? So the probability of accepting Sk plus 1, given that Xk plus 1 belongs to the n of Sk. N of Sk means neighboring of the solution Sk. So the probability will be 1 because this is a better solution. So better solution means we have to accept directly. Right? If this is not a better solution, else, so how to find out that probability? So the probability of accepting Sk plus 1, given that Sk plus 1 belongs to the n of Sk, this equals to, here you have to find out the, right, the change in energy, exponential of change in energy, right? Minus f of Sk plus 1 minus f of Sk. Objective value for the neighboring solution minus your objective value of the current solution, right? Divided by T. T is the control parameter here or the temperature, right? So always you will get the value in the range 0 to 1. Again, now you are getting this acceptance probability now, right? Whether it's in the range 0 to 1. So how to determine whether you have to accept or you have to reject? So for that, what you have to do? You have to generate a random number again for every iteration. That's why from the first slide I told you this is a right your stochastic algorithm. So many randomness is there, right? So many random numbers we are generating to take some decision in order to move the solution from one point to another. Right? So what you have to do, you have to generate a random number here again Rk for every iteration or at each iteration k, the range 0 to 1, right? If this random number Rk is less than that acceptance probability, right? If this random number is less than this probability, that means this acceptance probability is very high, right? That's why you are accepting the neighboring solution. Otherwise, you have to reject the neighboring solution. If you are rejecting the neighboring solution, what you have to do? Again, you have to choose another solution from the neighboring set and you have to repeat the same procedure. Right? And the temperature you have to decrease, right? As per the annealing schedule, whatever annealing schedule, small t value, and by how much you have to change the temperature, as per that schedule, you have to decrease the temperature. Okay? So the temperature schedule decreases the probability of acceptance as the number of iterations increases, making your Ti progressively smaller because we are decreasing the temperature after every T number of accepted iterations. So whenever this T value is very small, right, very low value, at that scenario, we have to stop our algorithm. Now let us solve some small problem for this job sequencing problem by using this simulated annealing algorithm. So what is the problem here? There are n number of jobs are there. So here 4 jobs are there. Every job processing time in respect to days, right? 10 days are required to process the job one. Like that it is given. Or you can change the unit also to minute or seconds, right? So this is the due date or the due time is there for every job. Fourth column is the holding cost per day. That means if the job is processed, right, before the due date, so some holding cost you have to pay per day, right? For each job, that values are also given. And the last column, it represents the penalty cost. So penalty cost means if a job is completed, and then you are able to complete the job after the due date, right? So that means you have to give some penalty cost with respect to that job. So what is our target? Our target is to sequence the jobs, right? In the we have to sequence the jobs in such a way that the maximum cost, right, it will be minimized. So this is a minimization problem. You have to minimize the holding cost or penalty cost with respect to a job sequence, right? So how to solve this problem now? So what is the solution, right? How to choose a initial solution, how to apply the neighboring function to find out the neighboring set, how to choose the neighboring solution from the neighboring set, then acceptance probability, then your random number generation, right? Then depending upon the random number generation, what you have to do, you have to determine whether you have to accept a neighboring solution or you have to reject a neighboring solution, right? Now let us see how to formulate this problem with respect to your simulated annealing algorithm. So these things already I told. Each job J has a processing time Tj and due date Dj is given. If J is completed earlier than its due date, right? So a holding cost Hj for unit time is incurred. If the J is completed after its due date, penalty cost is incurred. So objective is to sequence the job such that total cost, your holding cost plus penalty cost of the job sequence has to be minimized. So this is a minimization problem. So how to find out this cost, holding cost plus penalty cost? If you see, suppose we will process in the sequence, suppose we have formulated the sequence as 1, 2, 3, 4. That means job 1 has to be processed first, then job 2, followed by job 3, followed by job 4. So how to find out the cost with respect to this sequence? So job 1, the processing time, this is 10 days, right? So first we are starting this job 1. So it will take 10 days. So due date is 15, right? So this is completed before the due date. So 5 days, for 5 days you have to give the holding cost. That means 5 into 3 plus second day, second job it will start from 10, right? And 8 processing time is 8 days. So it will complete in 18 days. For the due date is 20. So for 2 days you have to pay the holding cost. So plus 2 into 2. Next, the third job, it will start at 18. 6 days it will take, it will complete at 24 days, but the due date is 10, right? So 14 days penalty cost you have to give. So plus 14 into 10. Next, the fourth day, fourth job, it will start at 24, it will take 7 days, it will complete the 31. So 30, due date is 30. So for 1 day you have to give the penalty cost. So 1 into 8. So total cost in this way you have to find out. So your target is to sequence the jobs in such a way that the cost, right? The total cost should be minimized. So how to solve this problem? Let us see. So let us define the terminology related to the simulated annealing algorithm. Assume SK, this is the solution. So what is our solution for this given problem? Job sequence, right? So SK represents the job sequence used in the iteration K. N of Sk, this is the neighborhood sequences of S of K. So you have to apply some neighboring function to find out the neighboring sequence of Sk. Then you have to find out the temperature schedule, right? What will be Ti for every ith iteration. Then what is the total cost? That is the Ck, total cost for a sequence Sk. So this Ck value we are trying to minimize, right? So this Z0 is the, all right, whatever the initial solution we are considering S0, the objective value of S0 is the Z0. Why this Z0 is required? To initialize the temperature value. So temperature T0 equals to, we are generating a random number in the range 0 to 1. Suppose, yeah, this is the assumption only, right? You can fix a high temperature value also. So T0 is 0.5 into Z0. Then how to change the temperature? That's in annealing schedule is that we are decreasing the temperature by half after 3 accept iterations. That is the meaning. Ti equals to 0.5 into Ti minus 1. Then small t equals to 3. I mean after 3 accept iterations, we are going to change the temperature. So now your terms, right, terminology related to the simulated annealing algorithm we have formulated with respect to this job sequencing problem. Now let us see how we are moving from one solution to another solution here, right? So that this slide, it represents the same thing, whatever I told. Suppose I am choosing a initial solution as 1, 2, 3, 4. That means in this order I want to process the jobs, right? So the total cost as per discussed, right, as per the holding time, processing time and the holding cost per unit time, penalty cost per unit time, you will get the total cost for this sequence equal to 167. Right? Already I told you this. So Tk, you have to initialize the temperature. How to initialize the temperature? Because we have fixed this annealing schedule like this. So 0.5 into 167. So 83.5 is the initial temperature. Or you can pick some higher value like 200, 300, like that also you can fix. Then how to find out this neighboring, right? Because Sk is the current solution. So what are the neighboring solutions in the N of Sk, right? So as this is a job sequencing problem, so what are the possibilities, not the way in which you can find out the neighboring solutions? Only possibility is that we can swap these two orders, right? So 1, 2, 3, 4 is there. Simply what we will do, 2, 1, 3, 4. 1, 2 are swapped. In the next, maybe 2, 3 are swapped. 1, 3, 2, 4. Next, 1, 2, 4, 3, right? So you may swap also 1, 4. That is the 2, 3, 4, 1 also you may get another solution, right? So this is the neighboring solution you are getting. So this neighboring solution, right, N of Sk, I told you, it depends upon the problem. You have to think about what are the possible ways by which the different solutions can be framed for that particular problem. So for this job sequencing, you can add another also, right? Here 1, 4 also you can extend here, so that you will get another solution 2, 3, 4, 2, 3, 1. If you swap 4 and 1, right? This is only consecutive jobs I have swapped, right? Then what is the change is the energy? Change is the energy, I means the objective value of Sk plus 1 from the neighboring set minus objective value of the current state, that is the Sk, right? So what you have to do, you have to choose a randomly neighbor from the next solution, right? Then if you check whether the next solution is better, you have to directly accept because the probability will be 1. If the next solution is inferior, you have to find out the acceptance probability. Right? Now let us solve the problem. So at the iteration 0, suppose we are having the sequence, right? We have the initial solution as 1, 2, 3, 4. That is S0. S0 is 1, 2, 3, 4. So the total cost I told you how to calculate, right? So the total cost is 167. Our target is to minimize this one. So the initial temperature we have fixed with respect to 83.5. So whatever, we are not taking any decision here because whatever current solution or the initial solution is there, from that point we are trying to explore the solution space, right? So what we have to do here, we can see the last column. Last column represents the neighboring set of the solution Sk. So whatever I told you, only 2 consecutive jobs I have swapped. So this is the neighboring space of the solution 1, 2, 3, 4. So there are 3 solutions are there in the set. So how to choose which solution you have to choose? Randomly you can choose any solution, right? So for randomly choosing the solution, this R2k is used. This random number R2k means for the kth iteration, second random number, right? So you can design, right? Because you can design in your way so that one of the solution from the neighboring set can be selected. So here what I have done, if the random number I am generating is less than 0.5, right? If less than 0.5, I am considering the first one. If it is between 0.5 to 0.6, I am considering the second one. If it is above 0.6, I am considering the third one. Simplicity, because this is a very simple problem. 3 solutions are there, right? So this is the use of the random number 2. R2k is used for selecting one of the solution from the neighboring set. And if you see this R1k, this is the random number you have to generate for every iteration to determine whether you have to accept the inferior solution or you have to reject the inferior solution. So these are the uses of these 2 random numbers. And decision means whether you have to accept the next solution or you are going to reject. And this exponential minus z, right? This is the acceptance probability that I told you. Exponential of minus z by t, that value, right? So here if you see, this is the initial solution. Now I have generated 0.54. So the second solution I am selecting randomly. So this is the 1, 3, 2, 4 now. Again for this sequence, you can calculate the total cost. So if you calculate from the given example, you will get 171. So this is a minimization problem. So 171 is greater than 167. So this is not a better solution. So you have to find out the acceptance probability. That means e raised to the power exponential of minus 171 minus 167 divided by 83.5. So we'll get 0.96. Now you have to decide whether you have to accept this inferior solution or reject depending upon this random number. So you generate a random number in the range 0 to 1. So these are the randomness in this simulated annealing algorithm, right? So due to this random number, you may reach towards the global optimum or you may not reach also, right? Next, as 0.56, this is less than 0.96, so you have to accept the inferior solution. We are accepting. So here you see this small t value, you initialize this as 1 because here we are getting the first accept iteration, right? Because small t value, if you remember, here we have fixed this one. Small t equal to 3 accept iteration. After 3 accept iteration, we are going to change the temperature by half, right? So here small t equals to 1. Again, now what you have to do, we have to find out the neighboring of this 1, 3, 2, 4. Again, you apply the same procedure, you will get the neighboring solution here. Again, you generate a random number, I assume 0.74. So randomly we are selecting the third one. So 1, 3, 2, 4, 1, 3, 4, 2. Now calculate the total cost, that is the 345, right? Again, 345 is inferior than 171. Again, you find out the acceptance probability, right? Again, you generate a random number 0.34. You see here 0.34 is greater than 0.1. So we are rejecting. So here I have taken all the combinations so that you can know what will happen for every scenario. So here you are rejecting. If you are rejecting, that means you are rejecting the solution 1342 from 1324. So what you have to do, you have to do resampling here. That means another neighboring solution you have to select from this n of sk. So how to select? Again, you generate another random number. Suppose this is 0.19. So the first solution again you are generating from this one. Again, you have to proceed in the same manner. So if this is 3124, total cost you are getting 126. So 126 is better than 345. So directly you have to accept. Now small t equals to 2. Okay. Again, you follow the same procedure here. Right? Generate a random number 0.61. So second solution you are generating. Here you are getting 130. Again, 130 is greater than 126. The acceptance probability is 0.96. Right? Now you generate a random number to decide whether to accept this solution or to reject. So as you are generating 0.64, right? So 0.64 is less than 0.96, so you accept. Now t equals to 3. Small t equals to 3. 3 accept iteration over, right? Again, from this 3 to 1, 4, you have to explore the space, right? So again, you find out the neighboring. Again, you generate a random number. Suppose you are getting 2, 3, 1, 4. Now you see, for this fifth iteration, the current sequence is 2, 3, 1, 4. Its value, objective value of the cost is 162, which is higher than 130, right? So what you have to do here, this temperature column, right? So now your 3 accept iterations are over. So you have to change this temperature. So by how much you have to change the temperature? Because you have scheduled the annealing schedule like this. Every 3 accept iteration, you are changing the temperature by half, 0.5 into Ti minus 1. That's why the temperature will be here 41.75. That is the half of this 83.5. Again, you repeat the same procedure, right? So this step, right? So this I have shown for hand calculation only for 5 iterations. So if you do the same steps for multiple number of iterations, there is a chance that you may get the best or the global optimum solution. So for this particular problem, for 5 iterations, here you are getting the best solution, right? At the iteration 3, you are getting 3, 1, 2, 4 with the cost, right? The total objective value is 126. So the objective or the optimum job sequence, right, for this particular problem is up to 5 iterations, you are getting 3, 1, 2, 4, right? So in this way, you can formulate a given problem by using the terminology of the simulated annealing algorithm, and you can solve the problem, right? So this is another problem. Here, this is the famous, right, your traveling salesperson problem. So many methods are there to solve this problem. So let us see how simulated annealing algorithm you can use to solve this traveling salesperson problem, right? So this is also 5 city problem. So there are 5 cities. The distance between every city is given. So your target is that, and there is a traveling salesperson is there. He has to travel from one city. He has to travel each and every city exactly once, and he has come back to the original city. This is the simple problem. So the distances between the cities are given, right? So how to apply this simulated annealing to solve the problem? So what is the possible solution? One of the possible solution for the given problem, the sequence of cities to be visited, right? Suppose the person starts from city 1. So 1, 2, 3, 4, 5. Again it has to come back to the city 1. So there has to be a round tour for this TSP problem. So how to formulate? So only one thing is there, you have to formulate the neighboring solution. How to formulate the neighboring solution? So in the traveling salesperson problem, the neighboring, you can perform the neighboring by using the reversal technique, right? So you have to pairwise reverse the cities in the traveling salesperson problem. So what are the components of the simulated annealing algorithm here? First, you have to find out the starting two. I mean the starting two, right? That is what is the initial solution of the given problem. So you can consider a specific two, or you can consider a random two, right? Soft tool reversal you have to do for finding the neighboring of a two. Then you have to temperature schedule. You have to do the annealing schedule, right? What is the starting temperature? And by how much you have to change the temperature, and after how many accept iterations you have to change the temperature. If these three things you are able to formulate, then you can solve the problem by using the simulated annealing algorithm. Now let us see how in this tabular structure I have represented how to show this solution of the TSP. Assume, so this is the iteration. First column represents the iteration, second column represents the reversal. Reversal means for determine the neighboring solution set of a current tour, we have to apply this reversal. Right? So I will explain you. Next, the third column, this is the tour. So assume 3, 2, 5, 4, 1, 3. This is the starting solution of the starting tour of the TSP. Right? Then what is the length? Because our target is to minimize the length also, right? Tour length you have to minimize. So this is the current length. This is the next iteration length. Assume the temperature T we have fixed as 50. Then P is the probability, acceptance probability of the inferior solution. R is the random number depending upon which we are going to decide whether you have to accept the inferior solution or you have to reject the inferior solution. Then depending upon that relation between R and P value, we are going to take a decision whether you have to accept the next solution or you have to present in the current solution. So this is the layout of this solution of the TSP using the simulated annealing algorithm. Now let us see what happens in the next iteration. Now 3, 2, 5, 4, 1, 3, this is our current 2. So we have to find out the neighboring. So how to find out the neighboring set? So for that, your pairwise reversal we have to do. That means 2 cities we have to exchange. Now you see 3, 2, 5, 4, 1, 3. So 2, 5 were altering, right? 2, 5 we are swapping. So we will get 3, 5, 2, 4, 1, 3. Next 5, 4 we can reverse, right? So 3, 2, 4, 5, 1, 3. Then 4, 1 you can reverse 3, 2, 5, 1, 4, 3. So can we swap 1, 3? Can anybody respond? Can you swap or can you reverse the city 1, 3 from this 2, 3, 2, 5, 4, 1, 3? Why I have taken only 3 pairs of reversal here, 2, 5, 5, 4, 4, 1. Why not 3, 1, 3? If you reverse 1, 3, you will get another solution 3, 2, 5, 4, 3, 1. But that is not a feasible solution because the starting city and the ending city should be same, right? So if you see the neighboring set of this 3, 2, 5, 4, 1, 3, the starting and the ending, right? There should be a round trip. So 3 are there. That's why you cannot consider 1. Similarly, 3 order you can do the reversal. 2, 5, 4 you can reverse, right? So that you will get 3, 4, 5, 2, 1, 3. Again 5, 4, 3 you reverse, you will get 3, 2, 1, 4, 5, 3. Similarly, you cannot reverse 4, 1, 3. If you take this 4, 1, 3, again this will become an infeasible solution, right? Lastly, 4-way reversal you can do 2, 5, 4, 1, right? So 2, 5, 4, 1 if you do, so you will get 3, 1, 4, 5, 2, 3. Right? Similarly, you cannot do 5, 4, 1, 3. You cannot reverse 5, 4, 1, 3 sequence. Again, you will get an infeasible solution. Right? So in this way, you can apply these reversal techniques to this TSP problem to find out the neighboring set. Now you are having the neighboring set or the neighboring solution for this tool. Now you have to randomly choose, right? So instead of randomly choosing one solution, what you do, you find out the best solution, or you can use the random solution also, no problem. So here, what methodology I have followed, I have chosen the best solution from the random set, right? So best solution is 725 now. 725 is minimum, right? So if this is the solution, right, 725 for this tour, what I have to do, I have to accept, because 725 is less than infinity. For the first two, the length is infinity. Maybe there is no path from one city to another city in this sequence, right? Because I have randomly selected the two. So the 725 is better than infinity, so I am accepting here. So your small t equals to 1. So here you keep a track of this t value, right? Next, what you have to do, now your current solution will become 321,453, right? So for 321,453, again you do this reversal and you will get the neighboring set. Again you find out which one is minimum from this. So out of this, 735 is minimum, right? So previously you got 725. Now if you are exploring the neighboring, you are getting 725, right? Sorry, previously it was 725, currently you are getting 735. So this is not a better solution. So we find out the probability of acceptance, that is the e raised to the power minus 735 minus 725 divided by 50. So we'll get 0.8. Now whether you have to accept this solution, you have to reject. So you generate a random number now, 0.85. As 0.85 is greater than 0.81, so you reject this one. Okay, so if you are rejecting this one, you have to resample, right? Resampling means you have to choose another solution from the neighboring. So as we are selecting the best solution from the neighboring, so after 735, next solution is 745. So 745 again, it is inferior than 725. Again you find out the probability 0.67. Random number, generate a random number 0.37. So 0.37 is less than 0.67, right? So you accept. Now your small t equals to 2, right? So for this problem, I have considered the small t value equals to 2. That means I am changing the temperature after 2 accept iterations, right? The next iteration you see, similarly this solution I am considering here, 3, 4, 1, 2, 5, 3. Again you find out the reversal procedure to find out the neighboring set, right? So from the neighboring set, you see the temperature column, this value is changing, because I have fixed the annealing schedule that after t equals to 2 accept iterations, I have to change the temperature by half. Now your temperature is 25, right? So same procedure you apply, and after only for the hand calculation I have shown for your 3 iterations, and you are getting here the 725. This is the optimum solution. And what is the sequence of cities the person has to visit? It will start from the city 2, right? Then 2, sorry, he will start from the city 3, then 2, 1, 4, 5. Again he has to come back to the city 3, and he is getting the tour length as 725, right? So this process you have to continue till your termination criteria is reached. So the termination criteria you can fix as, right, your number of iterations or some threshold value. Up to this threshold, tour length is sufficient, right? You can, or there is a no change is the optimum tour, right? In that scenario, you can stop the process, right? So in this way, you can solve this TSP problem by the simulated annealing algorithm. So this is another problem. Some assignment problem is there, right? Suppose there is a there is a problem to schedule the timetable or develop the time schedule, right? For 1 day, 5 period timetable you have to schedule. So there are 5 classes are there: C1, C2, C3, C4, C5. There are 5 teachers: T1, T2, T3, T4, T5. So these are the preferences given by the teachers, right? So the teachers provide the following preferences for teaching classes. So top of the list is most desired. So for teacher T1, he is giving this preference list as C2, C3, C1, C5. Similarly, T2, T3, T4, T5. All the teachers, they are given 4 preferences, right? So you can apply, right? Your genetic algorithm also you can apply to solve the problem. So first you have to find out the objective function. What you are trying to do, right? Well, what you are, whether this is a minimization problem, this is a maximization problem. If minimization, what you want to minimize? If this is a maximization, what you want to maximize, right? If that is clear, your objective is clear, then you can formulate the problem as per your genetic algorithm or simulated annealing algorithm to solve the problem. You can try to solve the problem. So I will share the slide so that you can solve the problem by using genetic algorithm as well as by using the simulated annealing. So these are the some of the basic applications, right? Because your participants are from different domain, so I'm not explaining any problem related to any specific domain, right? So these are the some of the few applications you can search for your domain how simulated handling has been applied to solve the problems, right? So optimal route detection between the objects, okay, and the wireless sensor network, your transport infrastructure planning for the civil engineering, right? The clustering also you can do by using the simulated handling algorithm, right? These are the, some of the references you can go through, right? So the PPTs are prepared from this book only, right? And these are the some of the applications of the simulated handling with respect to your image processing, right? And this is for the combination of genetic algorithm and the simulated handling algorithm. This can also you can see how, right, how different types of optimization algorithm people are combining to find out the optimum solution, right? So this is all about the simulated handling algorithm. If you are having any doubt, you please ask, then I will move towards the ant colony optimization. Any doubt with respect to simulated handling algorithm? I have some Python code for this simulated handling algorithm also, right? So the code is for solving the TSP by using the simulated handling algorithm. Just 1 minute, let me open the file. Okay, so I'm not explaining the whole part, right? If you are having knowledge in Python, you can explore. We'll share the codes so that you can see what is there. Right? So the traveling salesperson problem is solved by using the simulated annealing algorithm here. So here the simulated annealing part is there. So in this program, the traveling salesperson problem is solved by using 4 different techniques, right? Random distance, random weightage, right? And it is compared with the simulated annealing algorithm. And it has been observed that simulated annealing algorithm is able to provide good result, right, for the traveling salesperson. So these are the cities from A to M. These many cities are there. 12 cities are there. These are the indexes. Distance between the cities are given here, right? So for this, your right 1 minute. Let me go to the simulated annealing part. So here, this is the simulated annealing part is written here. Okay. Sorry. You can go through the code so that you can understand. So this TSP, traveling sales problem, it is solved by using best solution by distance. As per the distance, right, the solution to the TSP is determined. So this is the best solution by distance, starting from city F and the ending city F. In between all the cities, remaining cities are there, exactly once. So total distance is 8,706, right? Then the best random solution, randomly one city is selected. Again, started from, always the starting solution is F only, F considered, right? So F to F, right? But you see the cities, right? The cities selected are different for the first one, the second one. Here we are getting the total distance as 10,955. Third method is best random solution with weight. So these are the different greedy strategies, right? Greedy method has been applied. So here we are getting again the starting city is F, ending city is F, 9,117, right? And if apply the simulated annealing here, so random, right? Your initial city we have considered F here also. That means the initial solution. And you apply the simulated annealing algorithm by using this reversal techniques for the TSP, you will get 8,601. So if you compare with the other 3 greedy techniques, simulated annealing algorithm is giving or it is providing the best solution for the traveling salesperson problem. So you can go through this course so that you can understand. Only the simulated annealing part you can see how this algorithm, right, how to calculate. This is this part is simulated annealing algorithm. right? How to schedule the temperature T, how to find out the neighborhood, right? How to find out the change is the objective function, how to find out the acceptance probability, and how to define the, depending upon the random number, whether to accept the inferior solution or to reject the inferior solution. Only these two, in this function it is there. The simulated annealing part is written here. So we'll share the codes. You can go through these codes and you can verify, right, how this is working. If you are having any optimization problem, or you try to solve that problem, right, that assignment problem I have shown in the last slide, you try to solve that problem by using this code also. You have to change some part of the code, right, because you have to formulate the neighboring function here. Neighboring function will be different, and I have to find out a neighboring solution from the neighboring set. That will also, it will vary from your problem. And your objective value, right, how to determine the objective value, whether this is a minimization or this is a maximization, it will also vary, right? So this is all about your simulated annealing algorithm. If you are having any query, any questions, you please ask. Then I will move towards the next algorithm, that is the ant colony optimization. Any questions, any queries from the participant side? Am I audible?
Yes, ma'am.
Yeah, you were.
Yes, sir. Any doubts, sir? Anything is there on the chat box?
In fact, ma'am, after this class, I will practice, and with kind permission from Honorable Coordinator, sir, I want to actually be in your touch so that, I mean, if there is any kind of problem in my side, I can communicate with you to solve that. Thank you very much, ma'am.
Okay, sir. Somebody, can I use this algorithm of selecting features from a data set, right? Selecting features from a data set, simulated algorithm, alone simulated algorithm will not work, right? So we have to use simulated annealing algorithm along with some other algorithms, right? So we'll discuss the ant colony optimization algorithm. That algorithm we can use to select the features from a data set. Alone simulated annealing algorithm, it will not work for selecting the features. Okay, if no questions are there, let me move towards the ant colony. Ant colony optimization algorithm. Right. So the feature selection from the data set, right? You can solve that problem by using this ant colony optimization algorithm. Now we'll see how this, what are the basic concepts for this ant colony optimization algorithm and what are the applications. And we'll solve the same TSP problem by using the SEO, and you can solve the same way. You can do the feature selection by using the SEO. Okay. So this is also a very old algorithm, right? This is introduced by Marco Dorigo in the year 1990. So this is a population-based meta-heuristic algorithm. A simulated annealing algorithm, this is not population-based, right? So this is a population-based meta-heuristic algorithm. And this is mimicking the foraging behavior of the real ants. So what the ants they are doing, generally when the ants, they will move from the nest, from their nest to the food, right? They will release some chemical substance, that is the pheromone on the ground. And depending upon the pheromone strength on that path, other ants will move that path, right? So how the remaining ants they will move? They will move according to the richer amount of pheromone on their path. So this pheromone strength or this pheromone trail, this will guide other ants to go to the food source. So real ants, they are capable of finding the shortest path from a food source to the nest without using any visual cues. Only they are having this pheromone trail value. By using this pheromone trail value, the ants, they can find out the shortest path. Right? So this is also very simple how the foraging behavior ants are represented here. Now suppose this is the nest, this is the food source. So the two ants, they start with equal probability. Assume this is the shorter path. So the first ant will reach the food source. Assume the first ant is reaching to the food source fast. Right. So what will happen next? That ant, it will return back to the food source, to the nest. So it will deposit some amount of pheromone, that substance on that path. So the third ant, what it will do? Now in this path, pheromone strength is more, right? Here nothing is there. Your pheromone strength is more. So the third ant, it will move this path. So the density of the pheromone on the shorter path is higher. due to which the next ant or the third ant, it will follow the upper path. Right? So this is the third ant. It is following the upper path. Right? So what will happen after some time, the third path, right? This is almost exclusively used by the remaining ants. So that's why if you see the ants, how they are moving like in line. So how they are moving in that line with respect to that pheromone or the substance, right, deposited by the ants on that path. So this foraging behavior of the ants, this is represented by the optimization algorithm mathematically, and that optimization algorithm is called your ant colony optimization algorithm. So what happens in the biological or the general ant foraging, the ants, right? So these ants represent the individual solution of the optimization problem. And what is the ant colony? As I told, this is a population-based meta-heuristic algorithm. So ant colony represents the population of ants, right? The pheromone trail. So pheromone trail, this is the modification of the solution. How we are modifying the solution, right? So this is the modification of the environment caused by the artificial ants in order to provide an indirect mean of communication with other ants. So how the ants they will communicate? I mean, one solution to the another solution, that depends upon the pheromone trail. And as we are considering that pheromone is a chemical substance deposited by the ants, so with respect to time, we are assuming that some amount of pheromone will be evaporated, right? So the pheromone evaporation, that is considered as the reduction in the pheromone level of a given path due to aging. So these are the terminologies for the biological foraging, and this foraging behavior is mimicked in this optimization algorithm, that is the ant colony optimization algorithm. Now, how to solve any problem, right? That may be feature selection problem or any optimization problem by using this SEO algorithm. So this SEO algorithm is also very simple, only two mathematical equations you have to use to solve the problem. So what you have to do, you have to assume that how many ants are required, how many nodes. So that problem you have to represent as a graphical structure. So each graph or each node represents one ant, right? So here you have to randomly place m ants on n nodes. So I will explain through an example so that you can understand what is this m, what is this n, how to place this m on n, right? So each ant will move to the next node using some probability. So for calculating this probability, we have to use some mathematical equation, right? Once or after every ant completes its tour, it will compute the tour length Lk, right? So whichever is shortest path, you have to update the pheromone state for that shortest path. So this process you have to iterate until your termination criteria is reached. So the termination criteria may be maximum number of iteration reached, or there is a stagnation. Stagnation means all ants are making the same tour. You are not getting any new solution, right? So we'll see with respect to the TSP, what is the ant, what is the solution, right? How to find out the tour length, how to find out this probability value, how to update this pheromone strength. We'll see those things. Okay? So there are some terminology you have to follow using this ant colony optimization also. So first one is this is the tau ij. This is the intensity of pheromone trail between the two nodes I and j. So here I have explained with respect to TSP. That's why I have represented cities I and j. So this is the pheromone strength between two nodes or the two cities I and G, or I and J, or somebody asked about the feature selection problem, right? Or between two features, feature 1 and feature 2, right? So there is another parameter alpha that is used to regulate the influence of tau ij, right? This is the range in generally alpha value is in the interval 0 and 1, right? As per the research. Then eta ij, that is the visibility factor. This is the reciprocal of distance between two nodes, 1 by dij, right? So if this is the TSP, the traveling salesperson problem, the heuristic is distance, right? If this is the feature selection problem, you can consider the information gain, chi-square value. Those are the heuristic, right? So the visibility, that is the eta ij, you can find out by taking the reciprocal of distance. Then beta is a parameter that can be used to regulate the influence of eta ij. Again, as like alpha, the value is in the range 0 to 1. Beta is also the range is 0 to 1, because there is no hard and fast rule how to assign the value of alpha and beta, because these are the parameters you have to use. If you change the parameter values, it will change the performance of the algorithm. right? So you have to do different types of experimentation, right, to find out or to properly tune the parameters value of this alpha and beta. Then another terminology you have to use. So these are the terminology you have to use in the mathematical equation of SEO, right? Then allowed K, this is the set of cities that have not been visited yet respectively. Suppose ant is in one city, so the remaining 2, 3, 4, 5, these are not visited. So you have to keep 2, 3, 4, 5 in this set allowed K. Okay. Now we have discussed, right, with respect to time, the pheromone, there is an evaporation in the pheromone. So we have to update the pheromone, right? So this row value is also in the range 0 to 1. This is the parameter to regulate the reduction of tau Ij, that is the pheromone strength, right? And delta Ij is the total increase of pheromone level on the Sij. So every ant, when they are returning from the food source to the nest, we have seen some amount of pheromone is going to be deposited on that S, right? So that value is delta Ij. How much amount of pheromone is going to be deposited? That means there is an increase in the trail level, right? Which is Ij. And delta Ijk, that is the increase of trail level on Ij caused by ant K. So this is the K stands for the ant K. So these are the terminology you have to follow, right? So I will come back to this flowchart because these equations, if I will tell now, you can't understand. So I will explain through an example. Again, I will come back to this flowchart. So here, this is the initialization of ants and the number of nodes. This second block, it represents the probability calculation, how the ants will move from one node to another node, right? Then tour length you have to find out for each ant. Then the fourth block, it represents how to update the pheromone stream. And the next block, right, fifth block, it represents to increment the number of iterations. And this is the 6 diamond box. This is used to represent for taking decision, whether to terminate or again you have to repeat the procedure, right? So I will come back to these equations after explaining that example. Now we'll say a small example. This is a 5 city problem also. So the distance between every city is given, right? So what I have to do, I have to solve this TSP problem by using this ant colony optimization method, right? So there are 5 cities. So I can construct a graph having 5 nodes A, B, C, D, E. Now the number n equals to 5. So the m value always you have to take less than equals to n. M, number of ants should be less than equals to n. So for simplicity, what we will do, if you keep more ants, right, so you can explore more space, more solution space, right, so that you may get a better solution. So that is the purpose of the number of ants should be less than equals to the number of nodes in the problem. So this distance matrix is given between every pair of cities. Next, what you have to do, you have to find out the visibility, eta, the notation eta. Eta is the reciprocal of distance, right? So this is A to B is 3. So the visibility between A to B is 1 by 3, that is the 0.33. So we are not bothering about this primary diagonal because we are assuming that between A to N there is no path is there. So we are not doing any calculation, right? So don't bother about this diagonals, right? So this is the visibility matrix you can determine from the vertical from the distance matrix, right? Next, what you have to do, you initialize what are the parameters required for the SEO. So the number of ants equals to 5 because, right, 5 nodes are there, 5 city problem. So initial pheromone strength you have to assume, right? What is the pheromone, initial pheromone within each age. So assume that is 1, right? So pheromone weightage alpha, beta, I told you alpha is the parameter to control the tau of pheromone strength and beta is the parameter to control the visibility, right? So alpha, beta for simplicity 0.7, right? This is Q equals to 1. This Q value is used to determine how much amount of pheromone is going to be deposited by each ant, right? That is the Q, that mathematical formulation is there depending upon the Q value. So basically Q by tour length, that is the Q by LK. This is used to determine how much amount of pheromone you are going to deposit on each age. And the last is the up to how many number of iterations you have to solve the problem. So these are the parameters you have initialized. By using these parameters, now we are having the distance matrix. From the distance matrix, we got the visibility matrix. We have initialized the pheromone matrix, right? Then number of ants we have initialized and the alpha beta value we have initialized. Number of iteration we have fixed. This Q value to determine the amount of pheromone, that also we have initialized. Now how to solve this problem? So what we will do now, we are having 5 ants, 1, 2, 3, 4, 5, and we are having 5 cities A, B, C, D, E. So randomly we have to select the first city for each ant. So ant 1 we kept in the city A, 2B, 3C, 4C, 5D. That means they will get 5 different solutions from this randomly placement. So ant 1 it will start from city A. So it will explore the next city by using the probability function, by using the probability calculation. Similarly, ant 2 will then it may follow another sequence. Similarly, up to ant 5. So at the end we will get 5 different solutions. So each ant will provide one solution, right? Now we'll see how to find out the solution. So this is the pheromone distribution. Pheromone strength, I told you, the initial pheromone value is 1. This we have considered. Initial pheromone tau for each age we have considered 1. So this is the one. So we are not bothering about the diagonal. We are not doing anything about the diagonal. Okay. Next. So what you have to do? So we have, so I will show you the calculation for one ant only. So the same thing you have to repeat for the ant 2 to 5, right? So we have seen that, or we have placed the ant 1 randomly on the city A, right? So if you come back to the distance matrix, you can know that. So there are 4 cities that can be visited from the city A. That is the B, C, D, E. Now ant 1 is in city A. So there are 4 allowed cities, B, C, D, E. If you remember one terminology I told, allowed J, right? So allowed J equals to your B, C, D, E. So whether ant 1 will explore the city B, city C, city D, or city E. So how it will determine, or how it will select. So for selecting one of the city out of B, C, D, E, it has to find out the probability. So what is the probability that ant 1 will select the city B after city A? What is the probability that it will select the city C after city A? Similarly, what is the probability that ant 1 will select the city E after the city A? So for this we have to use the probability calculation, right? So how to do this probability calculation? Let us see. Right. So this is the ant 1 it will begin the tour from city A. So there are 4 unvisited cities B, C, D, E that can be visited from city A, right? So the next city out of this B, C, D, E set can be selected based on the probability value. So how to calculate that probability value? So for calculating the probability value, you need the tau Ij value, you need the eta Ij. Because this tau Ij we have initialized to 1 for every s, eta Ij we have we have found out this value by taking the reciprocal of the distance, right? This value is there with us. Now how to find out? So alpha, beta, I told you these are the control parameters for pheromone strength and the visibility factor, right? So what you do, you calculate the tau Ij to the power alpha into eta Ij to the power beta, right? So for individual age, for individual city, now you see I am coming back to here again, I am coming, then I will tell you. So for J, if you see ant A, ant 1 is at the city A. So there are 4 cities that can be allowed after the city A, that is the B, C, D, E. So for the city B, you calculate tau Ij to the power alpha into eta Ij to the power beta. So tau value we have initialized to 1, pheromone strength, right? Alpha value we have considered 0.7 into this eta Ij, if you see that A to B, that is the 0.33 to the power beta is 0.7. So if you calculate, you will get 0.46. Similarly, for the C, you calculate same thing, but you have to take the S A to C, right? You will get 0.28. For the D, you will get 0.61. For the E, you will get 0.46. Now you have calculated this one, tau Ij to the power alpha into eta Ij to the power beta. For individual cities, you have calculated. Next, what you have to do? Your target is to find out the probability. So how to get the probability? So the probability of Pij, what is the probability that the ant will select the city J after the city I? That means the ant is currently at the city I. What is the probability that it will select the city J? So how to find out? Now you are having tau alpha, eta to the power beta is there with respect to individual city. You divide with respect to the sum. So you find out the sum of these 4 values now. So sum of tau to the power alpha into eta to the power beta is 1.8. So what is the probability that ant 1 will select the city B after the city A? 0.46 divided by 1.8. Similarly, for the city C, 0.28 divided by 1.82. For the city D, 0.61 divided by 1.82. For the point city E, 0.46 divided by 1.82. So same calculations are there here. So probability to go from city A to B, you will get 0.25, A to C 0.15, A to D 0.33, A to E 0.25. Right? Now these are the probability value we are getting. Right? So for which city the probability is higher? For the city D, the probability is higher. That is the 0.3. So the ant will select the next city as D. So currently, initially we have placed the ant 1 on the city A. Now the ant 1 is moving from the city A to the city D by using this probability calculation. Now same thing you have to repeat, right? Now from the D, right, you have to see the distance matrix. What are the unvisited nodes from the city D now, right? So for this particular example, there are 3 unvisited nodes B, C, E. Again, you follow the same procedure, tau alpha, beta to the power beta for individual B, C, E. You take the sum, right? Then you find out the probability to go from city D to B, D to C, D to E. If you see, so the probability from D to B is higher, that is the 0.51. So the ant 1, it moved from point or the city A to city D, then from city D to city B it is moving. Again from B, there are 2 other cities are there, C, E, right? Again you calculate those values, again you find out the sum of these values, again you find out same procedure you follow. So the probability to go from city B to C 0.41, B to E is 0.58. Again this probability is higher. So the ant 1 will select next city as E. So A to D, D to B, B to E. So after E, he has to make the round trip, right? So after E, there is no choice. So he has to move to the city C because one city is there. Another city is there remaining. That is a C he has to visit because the constraint is that the person has to visit each and every city exactly once, right? So after C, only the first city is remaining, right? So he has to come back to the city A. So this is the, if you follow this procedure, you will get the tour for the ant 1 as A, D, B, E, C, A. So this calculation I have shown how the ant 1 moves from the city A. Again, it came back to the same city A. So it made a round trip, right? If you see the distance matrix, then you can calculate the tour length for this tour, for this specific tour by the ant 1 is 70. You have to see the distance matrix, right? In the distance matrix, the values are given for each edge, right? 17. So you follow the same procedure for the remaining ones because we have kept the ant 2 on the city B, right? So now you see, if you follow the same procedure, there is a round trip done by the ant 2, B to B, right? The tour length is 16. Here for the ant 3, 16, ant 4, 18, ant 5, 16, right? So this thing, the each ant, they are moving from one city to another city. So these are the 5 different solutions we are getting in the first iteration. So each solution, what is the objective value? This is the tour length, the objective value. So what is our target? Our target is to minimize the tour length. So what we have to do now? So we have to update the pheromone now. So 5 ants are there. So there are different variations of the SEO algorithm. Right, so here we'll use the all the ants, they will get an opportunity to update the pheromone string, right? So every ant, they will get an opportunity to modify the pheromone value on the each edge. So how to find out that value? So I told you one parameter I have considered Q, right? Q value equals to 1. So Q by LK, that is the tour length. So that much amount of pheromone is going to be deposited by that ant. So ant 1, how much pheromone it will deposit? 1 by 17. On which edges? A, D, D, B, B, E, E, C, C, A. Similarly, ant 5, it will deposit 1 by 16 amount of pheromone on the edge E, A, A, D, D, B, B, C, C, E. Right? So now we'll see how the pheromone matrix will change. So whatever I told, same thing is written here. So each ant will deposit Q by LK amount of pheromone on every edge of its tour. That is 1 by 17 by ant 1. On the path, right, all the edges are there. Ant 2 1 by 16, ant 3 1 by 16, ant 4 1 by 18, ant 5 1 by 16. Now let us see how the pheromone matrix is changing, right? So initially, if you remember, that was everything we have taken 1. You forget about this primary diagonal, right? We are not bothering. So before updating the pheromone string, we discussed, right, there is a evaporation in the pheromone due to the aging or the time effect, right? So how the evaporation happens here, that is the 1 minus rho, because rho is the factor used to determine the evaporation of pheromone. So 1 minus rho, suppose by 0.5 the pheromone strength is evaporating. So initially it was 1, after evaporation everything is 0.5. Okay, so the diagonal you can keep blank also for simplicity. Because I have copy pasted the matrix, that's why these values are coming. You can keep blank. You can keep a hyphen here. We are not doing any calculation on the primary diagonal. So this is the evaporation matrix after the evaporation of the pheromone with respect to the factor rho. Right. Now what will happen? Now ant 1 will deposit some amount of pheromone, that is the 1 by 17, right? That is the amount is 0.0588, which is A to D. Now you see there is a change in the AD, there is a change in the DB, there is a change in BE, EC, CA. So the red color, it represents the change is the pheromone, or that is the update in the pheromone state by the ant 1. So whatever edges it has traversed, in those edges it has deposited 1 by 17, that is the 0.0588 amount of pheromone on those edges. So this is the modification of the pheromone strength by the ant 1. Similarly, ant 2 will do the modification on these 5 edges. Again, there are 5 changes in the pheromone matrix. By how much amount? 0.06. Right. Similarly, ant 3 will do this modification. Next, ant 4 will do this modification. Ant 5 will do this modification. Right. So what we are getting, we have started the pheromone matrix with the value 1. Now after doing one iteration of this SEO algorithm, we are getting this pheromone strength. Right. So this is the output of this iteration 1. Right. Next, what you have to do, you have to repeat the same procedure. Right. You have to repeat the same procedure along with, and the next iteration there are different variations. Right. In the next iteration, you can change the placement of the ants on the nodes also. Right. So you have to repeat the procedure until your termination criteria is reached. So after termination, right, you have to take the best solution, that is the tool having the minimum. So after suppose certain number of iteration, you may get like this type of solution. Suppose you are getting, right. So which one is the best solution? So whichever is giving the right your minimum tool length. Suppose you can go for the ant 2 or the ant 3. So this may be one of the possible solution, or this may be one of the possible solution. But you have to repeat until the number of iterations, so that your termination criteria should be satisfied. Right. So there are this is a simple SEO I have explained for the what you call, that is a TSP problem. So somebody asked, I think, for the feature selection, how to do the feature selection in a data set for the application. Right? In the machine learning algorithms, we are solving many problems using the machine learning or the deep learning models. So if your data, right, your dimension of the data is very high, you can reduce the dimension of the data by using this SEO also. Right? So feature selection is one of the problem here. So feature selection technique can be used in order to reduce the dimension of the data set. Right? If you do the feature selection, what will happen? It significantly reduces the spurious information. Those are irrelevant, redundant, or noisy. Right? So if you do the feature selection, your dimension is reducing, due to which good outcomes can be expected from the applications. Right? It may speed up your data mining algorithm. It may improve your machine learning performance. You may get a better result if you reduce the feature selection. So how to do this feature selection by using the SEO, right? So this is simply, right, what you have to do. Every feature you have to represent it as a node, and all node, you are assuming that all nodes are independent of each other. If some features are dependent on each other, then you have to group the features. Right? You have to divide the n number of features into different groups, and each group you can keep in a node. Right? So here we are assuming all nodes are independent, because this will not happen in every domain, right? Maybe some features, they are dependent with each other. So you can group them and you can keep in a single node. So the nodes, that is the features or group of features, they are selected according to the selection probability. I told you the probability function, right? So that probability function you can use to select the next set of features. So how you have to initialize here? You have to initialize the parameter alpha, beta, heuristic information. In the TSP, the heuristic information is the distance matrix, right? But in the feature selection, the heuristic, you can use the information gain chi-square value. Those values you can use as the heuristic to solve the problem. So for feature selection problem, right, how to keep the number of ants. We have to fix the number of ants, right? In the TSP, we have fixed your M, number of ants should be less than equals to N, number of nodes. But in the feature selection problem, as per the research, right, the literature, the number of ants case should be root over M, where M is a feature vector length. So root over M, 16 features are there, so you can consider the number of ants equals to 4. So each ant is propagated to one feature node or from one group of features to another group of features. So you can initialize the pheromone matrix, you can initialize all the required parameters, then you can construct the tool. Same procedure you have to follow. You can construct the tool, that is movement of the ants from one feature to another feature or from a set of features to another set of features. Then you update the pheromone strength, then you take the decision. Okay. Here I will come back to that flow chart of the SEO, whatever I have left. So there only the mathematical equations of the mathematical equations of the probability function and the pheromone update is written. So the probability function, right, tau to the power alpha into eta to the power beta divided by summation of tau to the power alpha into eta to the power beta. This is given 0 or 1 or 0, right? Then tour length you have to calculate, and this is the pheromone update. So pheromone update, there is a pheromone evaporation is there. So this is the tau yj t plus 1 minus rho into tau yj plus delta tau yj. How much amount of pheromone is going to be deposited by the reagent, right? So these two equations you have to use in the ant colony optimization algorithm to solve the problem. The same procedure you have to follow for the feature selection by using this ant colony optimization algorithm, right? So this is the same flowchart, is the same only. You have to randomly move all ants to different feature nodes. You have to initialize the initial parameters, pheromone matrix. You have to calculate the heuristic information, right? As with respect to TSP distance, here you can use the information kit. You can construct the process, that means as per the probability function, how the ants will move from one node to another, one feature to another feature, or one group of features to another group of features. Then you update the pheromone strength, right? Then all the k ants are moved, right? Then you can update the pheromone function here. Okay. Your update process means your ants, they will make the tool here. Now at the end you take the decision whether all the iterations are completed or you are getting some stagnation, right? There is no movement in the ants. In that scenario, you can stop here. Then you can select, you can decide, right, which features you have to select. So you have to find the selected features, a subset from the available features. Right? So decision process you can take by using the pheromone value only. Right? If the pheromone, you can keep some threshold value for the pheromone, and that threshold value for the pheromone you can use for selecting the features. So the pheromone value which is greater than the threshold, you can select the corresponding feature and you can generate the feature subset S. Right? Then you can use those feature subset S for solving a particular task. You may use for solving that you want to train a machine learning model or deep learning model, for solving any classification problem or solving any regression problem. Right? So there are different variations of the ant colony optimization algorithm. Max mean ant system is there, ant colony system is there, right? In the max mean ant system, what will happen? Only the best ant adds pheromone trails. Right? So either the ant that produce the best tour in the current iteration or the best so far ant is allowed to deposit the pheromone. So here whatever example we have considered, we have given a chance to deposit pheromone, right, by all the solutions, by all the ants, right? So in this variation, only the best ant, they will get a chance to deposit the pheromone, right? So you can initialize the minimum and the maximum values of the pheromone also, right? If the, like your bounding, kernel bounding we are using, if you during modification or updation of the pheromone, if it is right, it is coming beyond the maximum value, you can forcefully make it maximum value, and if it is coming beyond the minimum value, right, less than the minimum value, you can keep that as the minimum value. Right? In this way, you can do, right? Or if some pheromones, you can reinitialize it also. Pheromone stress can be reinitialized each time the system approaches stagnation. There is a stagnation, it is coming. That means there is no improved tour you are getting. So in that scenario, you can reinitialize the pheromone trail and you can process, right? Because everything depends upon whatever initial value of pheromone matrix you are considering. Right? Maybe whatever pheromone you have considered or you have initialized, it is not getting, it is not giving, it is not providing better solution. So you can reinitialize that value also, right, for getting better solution if stagnation problem occurs. In the ant colony system, there are global updating rule is there, local updating rule is there, right? So locally, you can ants will update the pheromone. Globally, also the ants will update the pheromone. Right? So the state transition rule provides a direct way to balance between the exploration of new agents and the exploitation of a prior and accumulated knowledge. Right? So exploration and exploitation, this will happen in the ant colony system. So the global updating rule is applied only to edges which belongs to the best ant, right? And the local pheromone, it is updated by every ant, right? So in this way also the ant colony system, it can vary, right, depending upon your global updation rule or the local updation rule of the pheromones. So there are several potential applications of this ant colony optimization algorithm, right? You can do routing, traveling salesman problem, we have seen, right? Vehicle routing, sequential ordering, connection oriented network routing, connectionless network routing, optical network routing. So these are the different domain, right? You find out for your particular domain what are the optimization problems, right? For your domain. And if you see if the problem is any with respect to routing, assignment, scheduling, subset, right? So which type of problem it is coming? Quadratic assignment, course time tabling, graph coloring, frequency assignment, project scheduling, car sequencing, or the job sequencing, right? Set covering, multiple knapsack, maximum different types of problems are there. You find out a particular problem for your domain and see whether this SEO help to solve your problem. So there are several advantages and disadvantages of this SEO also. So coming to the advantages, there is inherent parallelism we have seen, right? Because we are keeping multiple ants, right? Multiple solutions we are getting. So parallelism we are getting, right? So there is no central control in the colony, right? Because every ant, there is the variations of the SEO we have seen where every ant they are getting a chance to update the pheromone. So there is no central control. If you use the right global updation rule, there is the central control. But if you giving chance to all the ants to update the pheromone, right? So there is no central control. So positive feedback accounts for rapid discovery of good solutions. So this is efficient for TSP or the similar assignment type of problems. It can be used for dynamic optimization problem also, right? So coming to the disadvantages, theoretical analysis is very difficult here, right? So the sequence of random decisions not independent, that in the sequence of random decisions that we are taking by using the probability, right? Because the values differ from, if you take the different values of alpha and beta and the row value, right? Depending upon that, our solution will change. So the probability distribution, it is going to change by every iteration, right? So time to convergence is uncertain, but convergence is guaranteed. You will get a solution, right? So research is experimental rather than theoretical. So you have to do a lot of experiments, right? So proper tuning of this alpha beta value, row value, so that you can find out, right, what are the best values of this alpha beta and the row in order to get a better solutions, right? So these are the some of the applications of the ant colony optimization. Your sensor deployment in wireless sensor network, dynamic path planning. Okay. Again, there are, right, different combination of this ant colony optimization of the genetic algorithm, right? Because these are the basic algorithms, so you have to hybridize some algorithms so that you can get better solutions. So this is the single processor scheduling problem by using ant colony optimization techniques. I think this scheduling problem, Dr. Sanjay has explained using the genetic algorithm also, right? You can see how this type of problems can be solved by using the ant colony optimization, right? So this is all about the theoretical part of the ant colony optimization algorithm. Just 1 minute. We are having some MATLAB code also. Just 1 minute. Just what document? Okay. So this is the MATLAB code for your ant colony optimization algorithm. So here the main program is here only, right? So there are 4 functions are there. One is your how to construct the ant tour, okay? How to calculate the cost. I mean how to calculate the objective value, right? This function. And update the trace means this function is for updating the pheromone strength, right? So there are 4 functions. This is the main function mySEO. So this mySEO, this is calling ant tour for constructing the tools for finding the solution. Calculate cost for finding the objective value. Update the trace for updating the pheromone strength, right? So this is written for the traveling salesperson problem, right? TSP problem. So you can use this code, right? You can modify this code for solving any assignment problem also, for any job sequencing problem also, right? So here randomly we are selecting the student. So what we are getting here? You are some code, some cities we are considering as a traveling salesperson problem. So randomly it is assigning right distance between the 2 cities here. The first graph. Second one, this is the average of 2 distance by using this ACO. How it is coming, right? If you see after these 2 iterations, the average 2 distance is decreasing. Because this is a very small problem. Randomly it is initializing. Then what is the minimum cost of the total length? It is giving something 73 point something. So these are the, right, from this it is starting from this point, and these are the sequence in which the SEO is right, the visiting the cities present in the TSP, right? So the minimum cost you are getting 73 point something, right? If you see in this graph also, it is started from 18. After these iterations it is changing, right? Here it is coming around 73 points something. So you can go through this code, right? Because explaining each and every line of code is difficult, right? So you can see something if you have knowledge about the MATLAB, right? MATLAB, or you can implement the same using the Python also. Only you have to write these 4 functions. You have to how to construct the tour for the ants, how to find out the solution for an ant, you have to write one function. How to calculate the objective value, right? For that you have to write one function, and how to update the pheromone strength. For that you have to write one function, right? Then you call those functions inside the main, and you can solve your problem. Right? So this is all about the ant colony optimization algorithm from my side. If you are having any doubt, any questions,